It was way back in lecture number 9 that we first noticed that a mysterious stranger had wandered into our midst. This algorithm Heap Sort showed up in our table of sorting algorithms, and I said, oh, I don't know anything about Heap Sort. We're not going to talk about that today. But then Heap Sort kept showing up again and again, over and over again. We kept seeing this mysterious stranger, and I just kept saying, well, I don't know anything about that. Don't ask me. I'm not going to talk about that today. I guess the time has come for a bit of a reckoning. We sort of need to talk about heap sort. And I think that's going to be the final word on sorting for the time being. We're sort of ready to move on, but we really have to address this. And it's also a good opportunity to take a step into the future and begin talking about data structures that are based on trees. So this lecture is going to be about something called a heap. But first, I want to talk about an abstract data type called priority queue. And a priority queue has 3 operations. So ultimately, a priority queue stores a collection of elements. Now, there's some nuance to that. You'll notice I use the term key and I use the term element. I'll expand on that in a minute. But the 3 operations are, you can add something to your collection of elements, and then you can request at any time to get the element that is the minimum. Now again, the word minimum there is defined sort of strangely, the element with the minimum key. I'll come back to that in a minute. And then finally, you can ask to both retrieve the minimum element and to remove it. So those are the 3 operations that comprise the priority queue. Now, I guess the idea behind the name priority queue is that maybe there are those that conceptualize it as being an expansion of the typical classic queue data structure. So recall that in a classic queue data structure, we sort of think of it as, getting in line or something, and the first person to get in line, so if I add some elements to my queue, the first person to get in line is the first person to get to the front of the line. And we refer to this as being first in, first out order. And so the only thing that dictates the position or the when you get out of the line is when you got into the line. That's the only factor that determines it. But we can think of a lot of cases where we do want to maintain some orderly ranking of things, so some collection of objects where we want to be able to pull out the thing at the front of the line at each step, but we do want to allow the actual structure of the line to sort of shift based on, I guess, priorities. There could be cases where we want one thing to get accelerated and be allowed to budge in line. Now, I don't in general agree with the idea of budging in line out there in the real world. I have to make that very clear, but there are cases where we have some set of objects where we want to process them all one at a time or something, but the order in which we process them isn't strictly based on the order in which they arrive. So one, I guess, classic reference example for a case where you might want a priority queue data structure instead of an ordinary queue is, suppose you're an operating system and you're trying to schedule a set of processes. Now this actually applies to any task scheduling situation, frankly, because there could be cases where some tasks are more important than others. But suppose you're inside the operating system and you've got a bunch of different processes that are running on the operating system right now, and your job is to implement time sharing. So you have to give each process that's currently running a slice of the CPU's time to run. And the thing is, there are some processes that are more important than others. Some processes that need to run at a certain interval to get things done. Some that are more urgent. So there are certain, I guess, operating system services that need to have priority over the processor's time. Additionally, and you may do this when you run tasks, there could be tasks that are deliberately defined to be low priority. So tasks where you know when you run it that it's not that important that it gets done quickly, it should just take up any idle CPU time. But you don't mind if it gets put on the back burner if something more important arrives. And the thing with this set of tasks, like a set of processes being run in an operating system, is that new ones could be created all the time. And so it makes sense to think about this as a data structure problem instead of an algorithm problem. With an algorithm, so think of a sorting algorithm, for example, you could easily take a collection of things, if you know all of them in advance, and you could rank them by any criteria you choose. You could define some comparison operation that ranks them. The issue is, if we're thinking of a set of tasks where new tasks can appear at any moment, I could already have a set of 100 tasks, and I'm working through those tasks, and then 10 new tasks could show up halfway through. And I want to make sure that if one of these 10 new tasks is very urgent, that it is the next thing in line. So it's allowed to cut in line and advance to the front of the line quickly. So task scheduling on an OS is, I guess, an applied example of that. But if you want a thought example, so some thought experiment, think of you decide to open a package delivery business, and customers walk in and they have packages to deliver, and some of them pay for the discount shipping, which means that you deliver the package whenever you can, and of course a package that comes in earlier you try to deliver first. But if a customer shows up and pays for the expensive one-day shipping, their package gets advanced to the front of the line. And in general, I guess, if a customer shows up and pays you $1 million to deliver their package first, well, then I guess their package gets delivered first. And if they've done that, please stop listening to the lecture, go deliver their package, whatever. And so we can think about this as being a data structures problem because, again, new customers can walk in the door at any moment with a new package to deliver, and you have to find some way of ranking packages dynamically as they walk in the door. Okay, so then there's the question of what does it mean to rank them? And I suppose from those two examples, maybe it's clear that there might be more to your data than just the ranking criteria. So if you're an operating system running a bunch of processes, maybe each process has some priority value that tells you how important it is. Now, on a typical operating system, and I mean, I have a bias, so when I say typical operating system, I mean a Unix-based system, so Linux or something. Typically, the priority actually is going to be a lower number if it's a more important task. So you want to give it a higher number if it's less important and can be delayed until later. But in general, it might be some arbitrary integer value. So there could be not just one or two priority classes, but a whole bunch of different ones, like one for each possible integer value. So there's a lot of granularity there. But also, there's more to a task running on an operating system than simply its priority ranking. So if we actually think about the task itself, so here's some task T. Well, it probably has all sorts of data inside of it that's all irrelevant to my ranking process. It contains, though, some comparable value that tells me its priority. And we will take the convention in this lecture that a smaller priority value means it's more important, that it's more urgent. And I know that might seem like sort of an inversion of logic, but maybe think about it like this. The priority value is sort of the preferred end time. So if it's smaller, that means it's sooner and therefore should happen more quickly. And so a task might consist of some priority value, or in general, some criteria by which to rank the task. We're going to call this thing a key for the task, so we'll just call it K in general. But the task itself could also have all sorts of other data that is completely irrelevant to us as the people ranking tasks. And so the way we think about this is sort of that really from our point of view, the only thing we care about is this key. That is what we use to compare two different elements of our collection together. And the rest of the data that sort of rides along with the key, it's always there, but we don't care that much about it. So I sort of put it in parentheses. Maybe there's some other associated element data. So we should keep in mind that that's always possible, but for the rest of this lecture, and just in general when I talk about priority queues, because all we care about is the ranking by keys, I basically treat elements and keys as interchangeable. And it's easy for us, if we implement this, to add other data that sort of rides along with the key. We're going to see when we talk about some more advanced algorithms problems in, I don't know, give or take like 10 or 15 lectures from now, we'll see examples of using priority queues where we do have to attach additional data along with the key. Although there are lots of cases where the only thing in our priority queue is the key itself. That is, there is no additional data for the element. So for the rest of this lecture, I'm sort of going to treat the elements of the priority queue as if they're just some comparable key and that's it. But remember, it's very easy for us to attach some extra data to it that is irrelevant for comparison purposes, but does follow the key through the collection. So the first thing we do with any data structures problem, I think, is to see if we can implement the operations of the data structure using simple underlying implementations that we already know about. So because what I'm working with is fundamentally a collection of elements, then I guess it makes sense to try using a basic sequence type to implement it. Now, for the sake of providing some context, I have actually listed what would happen if I use both an unsorted and sorted array or list. Now, as time goes by, I'm going to do this less and less. I might just talk about unsorted sequence versus sorted sequence. But it's useful to have this context, I think. The reason I chose both array and list maybe is obvious, because if I'm going to use a collection type, and that's going to be a sequence, then I should consider both arrays and lists. The reason I chose both unsorted and sorted is it just seems to me, when I look at the operations of the priority queue, that this emphasis on finding minimums, so obviously the insert and remove thing means I might want to use a collection type like a sequence, but the emphasis on finding minimums sort of implies to me that there's some ordering criteria that I could exploit. And I think, okay, that implies maybe vaguely some connection to sorting, so maybe I'll try storing my collection as a sorted sequence as well as an unsorted one. Now, what we can observe from this is that of these three operations, and I guess I should say, I sort of view the minimum operation as like half of an operation. Because really, if I can do remove minimum, finding the minimum and not removing it, it has to be easier than that. So as far as the difficult operations, I sort of view it as two sides of one coin, insert and remove min. One observation I can make right off the bat about this is it makes sense that both insert and remove min are probably equally important in the grand scheme of things, because the number of removals I can perform is limited by the number of insertions. And if I perform an insertion and I never remove that element, it doesn't make much sense that I'm really getting my full value of the element. So it sort of makes some sense that I should expect over time the number of removals to be more or less the same as the number of insertions. Maybe a little bit less, but it makes sense that if I add lots of things to a priority queue, I probably will eventually try and remove all of them. Now, this is in contrast to other data structures, so including some we haven't seen before. So if we think about, we'll talk about binary search trees later, but binary search trees would have three operations: insert, find, and remove. And in a binary search tree, we could argue that the find operation might be a lot more important to optimize. So it's important for find to be fast, because there are conceivable use cases where I insert 1,000,000 elements to my binary search tree, and then I run find 1,000,000,000,000 times. Like, I could insert elements and run find over and over on the same element. And that is actually a common use case we can think of with searching structures like binary search trees. So in that example, I might consider that I probably want to make find as fast as possible, insert fast as well. I don't mind if remove is a little bit slower, because it's less likely that I do removals in the grand scheme of things for a lot of use cases of binary search trees than to do insertion or find operations. So in a data structure, there are occasionally cases where you can say, well, this one operation is the one I'm going to use the most often, so I should prioritize it. But this is not one of those cases. In this case, it does make some sense that both insert and remove min are more or less equally important. So I do want to try and find an implementation that keeps the running times of both of them relatively low. In other words, I wouldn't do a trade where I could find necessarily, if I could do insert in big O of n time, that I do remove in constant time, because it feels to me as if I'm just shuffling work between the two things. I want to find a way of reducing the running time of both of them. In any event, it is clear that I can make one of the two operations constant by choosing the right underlying storage. So we have the usual problem if we use unsorted arrays, where the worst case is big theta of n, because if we have an unsorted array that's full and I insert one new element, I have to resize the array. This only applies, though, in the case where the array size needs to be expanded. So the insertion time is constant if I've created an array that I can guarantee will always have enough space available. So if you tell me in advance the value of n, I could just create an array of that size and therefore never need to expand it. So you tell me the maximum size that my collection will ever take on. Okay, that's a bit of a fine point. So in any event, we can make insertion properly constant in all cases by using an unsorted linked list, because of course inserting into a linked list, especially in an arbitrary position, is very easy. Okay, so I can make insertion constant time, but in that case remove min has to be linear time, because in an unsorted list, the only way of finding the minimum element is to go looking everywhere, is to look at every single element of the list. On the other hand, if I chose to store my sequence of my elements as a sorted list, okay, well in that case, remove min is easy because the minimum will appear at one end of the list. If I do this with a linked list, then if I have the minimum appear at the beginning of the list, so if I'm sorting it in ascending order, then I just remove the first element and I'm good. If I store the minimum at the beginning of an unsorted array, well then to remove the minimum, I have to remove that first element, which could require shuffling n things over. Okay, so that would be linear time. But just to be clear, even if I tried some clever tricks, like sorting it in reverse order, where the minimum is stored at the end of the array, there are still cases where I would have to have a linear time operation. Because, for example, if I keep removing things from the array, eventually the array might need to be resized downwards. I might need to make the array smaller. And allowing for that possibility, so as not to waste too much space, that would also be a linear time operation. Although there are cases where you could come up with an implementation based on certain constraints that would be constant time for remove min. In any event, we do have this problem where ultimately, one end or the other, if we use I should have circled this. Sorry, we're talking about sorted sequences. I can make one of the two operations constant, but not both of them. And the other operation always seems to run in linear time. Now, another observation I make here is if I look at the comparison between unsorted and sorted, I sort of can find this weird duality that takes me back to insertion sort versus selection sort, which is that if I use an unsorted sequence, well then adding something is very easy. But then removing the minimum involves basically selecting the minimum element, which is a form of selection algorithm, although the slides are being a bit bombastic here. It's not like a selection algorithm on the order of quick select or the BFPRT pivoting or whatever, like none of that stuff from, what was that, like lecture 11? On the other hand, it is a selection process. It's similar in particular to one step of selection sort. That's what one step of selection sort does. It goes and finds the minimum element of the remaining sequence and then sort of extracts it, moves it to the front or something so it can be, in this case, it can be removed. So if I use an unsorted sequence, then the RemoveMin step boils down to, in a sense, one step of selection sort. On the other hand, if I use a sorted sequence, well then RemoveMin is easy. I just knock off one element from the beginning or end. But my insertion process is one step of selection sort. Okay, so what is this telling me? Well, okay, first, maybe by now you've concluded I'm sort of obsessed with the connection between insertion sort and selection sort. For some reason, I really love this idea that they're two sides of a coin, and that might mean that I'm some sort of crank. I mean, it could be that that's just me thinking that, and I just keep saying it over and over again in an attempt to make other people believe me. But what I think we can see from this, even if you're not as fascinated by the connections between insertion sort and selection sort as I am, is that there does seem to be a connection between a priority queue and sorting algorithms. It does feel as if this is a sorting adjacent problem. And if we think about it a bit more, it becomes clear that we can actually use a priority queue to do sorting. So if you give me some collection of elements, so here's a collection of n elements here, and let's make it less in order. Okay, so here's a collection of n elements, 4 elements. If I take this array and I make a priority queue and I just insert every value into the priority queue and then call RemoveMin over and over again, the first minimum I'll get is 6, then 10, then 17, then 187. So any implementation of a priority queue you can give me, I could turn that into a sorting algorithm by just doing n insertions followed by n RemoveMin operations. Okay, so that again emphasizes that what we're dealing with here is some kind of sorting related application. It's not quite a sorting algorithm because it's a data structure. And in a sense, you can almost think about it like some sort of sorting process that can be frozen in time, because I can call insert to add some elements, I can call RemoveMin to get a few elements of my sorted sequence, and then I can stop for a while and then call insert a few more times. So I'm allowed to sort of modify what elements are left to sort at any time during the process. And because it's broken into separate operations, it's pretty clear when I can make those modifications. So I guess where I stand on this is that in a sense, we have a sorting-related data structure. We already have tried the various, sorting approaches that are insertion sort or selection sort based. That is, these in a sense correspond to generalizing insertion sort and selection sort to the priority queue problem. And I think I want to make my priority queue operations faster. As I said a couple of minutes ago, in this case what I define faster to mean, given that insert and RemoveMin are both important, it seems to me as if they both need to have smaller running times. It's not, because if I just want to have a fast insert operation, well then I can get a constant time insert operation if I'm willing to take a big theta of n remove operation, and that would be fair enough. But what I want, I guess, is to reduce both operations to be less than linear running time. And that means asymptotically, of course. And so, well, what running times do we have on hand then? Well, I want somewhere between 1, constant, and n. And I want it to be less than n, so somewhere up to but not including n. And then as usual, I think, okay, well, having every operation be constant is too good to be true. It seems a little bit unusual. That would be very bizarre to have a collection that can store an arbitrary number of data items where I'm able to do this sorting adjacent operation where everything is constant time. And in fact, if I had such a data structure, that would violate the lower bound on comparison sorting algorithms. Since I can turn this priority queue into a sorting algorithm, if I were able to insert things in constant time and remove things in constant time, then my simple sorting algorithm where I do n insertions, so that would be n times constant time, plus n removals, that would be n times constant time, that would give me an algorithm that is big theta n, and it would be a comparison-based algorithm, and that's not allowed. Our lower bound says it's impossible. So actually, I sort of work backwards from that, and I'm like, wait a minute. If I use my priority queue to do sorting, what is the fastest that insert and remove min could possibly be such that I don't violate my lower bound? And we can think about it and realize that I guess the fastest I can expect these two operations to be is log n. Because then if I do n insertions and n removals, I end up with an n log n sorting algorithm. And I can't do better than that. We know that for comparison-based sorting, that's the best I can do asymptotically. So I guess my goal is, can I find a data structure that gives me log n performance on both insert and remove min? And the next question is, where do I start? How do I do that? Okay, so on the how, I guess what I would say is we already know that insertion sort and selection sort don't give us what we want. They give us something that's too slow. And in fact, if we actually engineer a sorting algorithm out of these implementations, it turns out to be n squared, unsurprisingly. I would even argue that we end up basically getting selection sort and insertion sort themselves. So I think, well, what other options do I have? Well, I could try basing my data structure on a divide and conquer sorting algorithm. Let's see if we can find a way of adapting a divide and conquer strategy to this priority queue data structure. Now, this is a bit tough, so I'm going to start with a thought experiment. Let's just think about what it would mean to use a divide and conquer approach on a data structure. So the issue here is that in a divide and conquer algorithm like merge sort, we have our entire input array at the very beginning. So it's very easy to say, let's cut it in half and divide it into two pieces. We don't really have that for this data structure because different elements can arrive at different times. So I guess what I have to do is maintain a persistent sort of division between elements. Okay, so how about this? Here's a thought experiment. Let's suppose we're halfway through working with a priority queue. So there's already a bunch of stuff in the collection, and we'll use that as the basis for our thought experiment. Suppose that I take the elements of my priority queue and I just throw them on the floor in two different piles. And the key thing, I'm saying a pile of numbers here because the numbers are not internally organized. I just break them up into two basically equally sized piles, jumbles of numbers on the floor. Okay, and this is a way of dividing them. And the idea behind this way, throwing them into a pile on the floor, is that if you add new elements, so if you say add the number 6 to this collection, I'll just throw it into one of the two piles. So at any time, so as I insert and remove, I have two piles that I hope are of roughly equal size of numbers. And so I've kept the elements of my collection divided into two pieces. And what I want to do is use this example to try and figure out whether there is some benefit to doing this. Whether if I want to now find the minimum of the collection, I can somehow do it faster as a result of keeping the numbers divided into two distinct and disjoint sets. Okay, one observation I make is that if I need to know the minimum of the whole collection, well then I have to go figure out, I have to look at the values in the two piles. One thing I could do though is I could just keep track of the minimum of each pile separately. And my instinct, the reason I want to do that is because if I assume, if I go back one, if I assume that there are n over 2 things in each pile, well then finding the minimum of each pile would just involve looking at those n over 2 things separately. That is, I don't care about the pile on the right when I'm computing the minimum of the pile on the left. And that does seem to be a bit of a benefit, versus if I go all the way back to here, if I have an unsorted sequence with all of my elements, then finding the minimum actually requires looking at all n elements. Now it's big theta of n, whether it's n over 2 or n, but certainly finding the minimum of the entire collection is going to take longer by a constant factor than finding the minimum of half of the collection. Although that isn't already a benefit because, of course, to find the minimum of the whole collection, I can find the minimum of this thing, find the minimum of this thing, and then take a look at the two minimums I come up with. That still takes n operations, obviously. But let's follow through on this. All right, so what I'll do is I'll keep track of the minimum of each of the two piles, and I'll just put it aside, because I know that I care about minimums in this case, so I'll just hold on to the minimum of each pile. I'll keep track of it separately. Now the question is, suppose I want to know the minimum of the entire collection, the global minimum. Well, using logic sort of similar to merge sort, I can observe that, of course, the minimum of everything will just be the smaller of the two minimums of each pile. Because obviously, if 3 is the minimum value of the pile on the left, nothing smaller than 3 is going to be in the pile on the left. And same thing with the thing on the right. So if I want to know the minimum of the whole collection, all I have to do is compare the two minima of the sub-collections. Okay, that's fair enough. So suppose I want to do that. And in fact, I know that finding the minimum is important. So in this case, maybe I'll say, look, I'll just keep track of the global minimum too. I'll just put it up here. Oh, that's an interesting way of drawing the diagram. So I'll just put the global minimum aside because I know you're going to want it in a minute when you call remove min. So I'll put it up here. And then I think, it still would be useful to keep track of the minimum of each pile separately, just in case I need it for something. Okay, so I can go over and recompute the minimum of the pile on the left. Now here's something interesting. To recompute that, once I put my global minimum aside, I now have n-1 elements left over. And I want to know the minimum of each pile. Well, the minimum of the pile on the right hasn't changed. I don't have to do any more work with the pile on the right because I haven't touched any of its elements. The only thing I have to recompute is what's going on the left. That only takes n/2 operations. Versus if I compute the minimum of a sequence and then delete it, I will then have to go through all n-1 elements if I haven't divided the sequence into halves. So here I was able to save a little bit of work. I only had to recompute the minimum of 1/2 of my elements. Okay, so that's a sign that I might be on the right track. Now, suppose you want to remove the minimum. So because I'm keeping the global minimum up here, it's pretty easy for me to give it to you and to delete it. So I do that. And I think, you might want the global minimum again in a minute. So maybe what I'll do is I'll promote one of the two minimums of the piles to be my global minimum. So again, that's just going to be 9. And I can do that by just looking at the two minimums. I don't have to look at anything else in each pile. Okay, so I can promote it. And then I can recompute the minimum of the thing on the left. And again, I don't even touch the stuff on the right. The only thing I have to look at are the more or less n/2 elements on the left. One hazard you might see on the horizon here, though, is that if this keeps happening, one pile might end up much smaller than the other. And so that's not really our immediate concern. We're still thinking about this divide and conquer idea, but certainly that's something we have to have on our radar. So what I've noticed here is that by maintaining my piles of numbers, I am able to avoid a lot of recomputation because I only actually modify one pile at a time. So when I go find the new global minimum, I'll pull out the minimum from one pile, and then I only have to recompute the minimum of the pile that I modified, not the other one. It can just stay put. And notice that nothing over here has been touched since I created my piles and first found the minimum of each pile. All right, another observation I can make is that suppose you tell me to insert something. So like I said a minute ago, if I say, insert the element, let's try inserting the element 100. Well, you could just say, yeah, just throw that in a pile. We'll just throw it over here. Okay, that might be a little bit of an oversimplification though, but certainly it's true that the number 100 could safely just be tossed into the pile on the left, down underneath everything else. There's a bit of nuance though. So suppose I told you I want to insert the value 10. Okay, well I can't just throw the value 10 down here into this pile because that would break a rule. Because I have set over here, I'm keeping track of the minimum element of the pile. So if I throw 10 in the pile, I've created a bit of an inversion because 10 is supposed to be, it is now the smallest element over on the left, so I should be keeping track of it. So what I could do is throw it into the pile on the left and then just check, is the number 10 less than the current minimum I have on file? If so, which in this case it is, I'll just swap it and I'll make 10 the current minimum and I'll bring 14 back down into the pile. So I could do that. And then there's one more case, which is suppose I want to insert the number 6. Okay, well I can start by putting 6 over here. And then I think, okay, well 6 is actually going to be promoted to be the minimum of the pile. All right, so we'll move 14 back down and bring 6 up. But actually, I have to go even further because 6 is actually less than my current global minimum on file. So I guess I'll do the same swap. I'll just take the 9 and I'll just throw 9 back down over into the left-hand pile and I'll swap it with the 6. All right, but that was a pretty small number of operations. I added an element, and all I had to do was I started it down here, and I swapped it upwards, and I swapped it upwards. That didn't require very many comparisons. I didn't have to compare it with any of the stuff on the right. I also didn't really care that much about all the other junk in the pile with it. I only cared about what was above it. Okay, that's all interesting. And I keep drawing these lines that connect things. I keep saying, yeah, I started down here, and I went up, and then I went up. And I begin to wonder whether there's some data structure that might help me with something like this. Okay, so as I said, we can insert by tossing something into a pile, although maybe some adjustments are needed. And so the case of inserting 43 is pretty easy because it doesn't interfere with any of these minimum elements. But I've already shown what happens if it did, and it would be a reasonably straightforward modification. So I think this is actually a good sign. Using this divide and conquer strategy, I am able to avoid a decent amount of work. So in other words, to recompute the minimum over here each step, I just do n over 2 operations instead of n. Now, n over 2 isn't that big of an improvement. It's only a factor of 2, which isn't asymptotically any better than n. However, I then realized that, of course, the big benefit of divide and conquer is applying the strategy recursively. So instead of just having literally 2 piles and keeping track of the 3 minimum values, why don't I have piles all the way down? I'll recursively subdivide each of the piles into smaller and smaller piles to try and leverage that benefit further and further. Okay, I think I've got the basic idea behind a data structure here. Now the thing is, if you want anybody to take your data structure seriously, you can't go around talking about piles of numbers. That sounds ridiculous. We need something more mathematical and formal sounding than just calling our data structure a pile. So we're going to call our data structure a heap. A heap is a binary tree which stores a set of comparable keys and where the structure of the tree has 2 additional properties that must be satisfied. You can see I'm talking about keys here, but when I draw the tree, I just draw into each node the value of the key. That is, there could be other data accompanying each node, so I mean it could just sort of be attached over on the side here. I don't really care that much. So that is, it is easy to implement a heap such that any other data that's irrelevant to the comparison, so the other data associated with the key, is attached to each node, and every time you move the key around, you move the data with it. We can do that, but for this lecture, I'm just going to treat the heap as if the only values stored inside of it are the keys, just to make things easier, because that's all we care about from the point of view of the heap. Okay, so a heap is a binary tree that satisfies 2 other important properties. And at a high level, these 2 properties govern A, that recursive divide and conquer thing that I mentioned a minute ago. That is to say, I would like it to be the case in a broad sense that smaller elements, and the minimum in particular, are easily available. What we're going to see later is that the minimum will always be stored in the root. And I want that property to apply all the way down, to apply recursively. In other words, even if I just look at a restricted subtree, that the minimum of that subtree is in the root. So one property governs that thing. Another property governs the fact that I want my tree to have a relatively small height, because that will mean that operations inside of it are fast. And so the 2 properties, the first one is called the heap property. And this is the defining characteristic of heaps in general, of heaps of all types. And the heap property states that if I look at the key stored in any node, so whether that be this node or this node or this node, the key stored in any node is less than or equal to the keys in either of that node's children. Or if the node has no children, then the property is vacuously satisfied. If the node only has one child, it only applies to the one child that exists. So if you notice in this tree, the heap property is satisfied everywhere. And that is what gives us, that's what allows us to realize the sort of recursive piles methodology we wanted before. That we keep the minimum on hand and everything below it has some order that is not relevant because it's sort of a jumble, but we need to have the order apply recursively. And so there is this property that sort of propagates all the way down the tree. The second property is called the shape property. And the shape property doesn't necessarily have to be a characteristic of this divide and conquer strategy, but we need it for later because it's going to allow us to say that our algorithms are fast. And the shape property states that the heap must be a complete binary tree. Remember that a complete binary tree is a binary tree that is a full tree up to the second to last level. So it has every node possible, no positions are vacant. And then on the last level, all positions are filled in from left to right. So there can be missing spaces, but they must all be on the right-hand side of the last level. And above the last level, there can be no gaps. Every node that can exist must exist. Okay, so, and of course, maybe it's clear that we can't simply define the heap to be a full binary tree. That is, a full binary tree is one that has nodes in every position among all levels that are populated. That won't work because our collection has to be able to store any number of elements, and we can only have a full binary tree if the number of nodes is a power of 2 minus 1. So a complete binary tree is the closest we can get to that, the greatest sense of order we can impose on that allows us to store any number of elements that we want. Now, actually, when I defined a heap a minute ago, I was being a bit too specific. The term heap is general, and there are lots of data structures based on lots of different flavors of tree that are technically heaps. So in fact, I can apply the heap property to different kinds of trees. You could imagine, for example, the heap property would apply even if every node in the tree had 3 children. So let's try this one here. So this thing is a heap if you define a heap to allow 3 children. If I were to allow up to 3 children, then I guess I could still define the heap property for that. There are other ways of framing the different styles of trees. So we talk about binary trees a lot. We've also talked about the idea that trees could have 3 children per node. There are other structures of tree that have sort of strange characteristic restrictions on the number of children of a node. We can still define the heap property for those trees, and therefore you could think of there being heaps that are not binary trees. We are not going to worry about that, but such things do exist. So the formulation of the heap that we use in this course is typically what's called a binary min heap. And I'll talk about what the word min heap means in a minute. But the key thing is, in this case, it's a binary tree. It's not some other exotic type of tree. And we're not going to worry about heaps defined on other kinds of trees. Although they do exist, we'll refer to them a couple of times, but we're not going to actually see any of them. And in this case, a min heap, and I'll talk about that in a minute, but it is true that the root stores the minimum key in the collection, but I haven't proven that yet. I could also talk about what's called a max heap. So this is a binary max heap. And in a max heap, all we've done is flip the heap property so that the key in each node is greater than or equal to the key in either of its children. And we will occasionally use max heaps, but they'll always be binary trees. However, in this course, if I say the word heap with no qualifiers, I always mean a binary min heap. It's always a min heap and it's always a binary tree. If I say the word max heap with no other qualifiers, then I also mean a binary tree, which is a max heap. So we won't use max heaps that often, although they're equally valid as min heaps. I mean, there are people out there teaching algorithms courses where all they talk about is max heaps, and that's fair enough. It's the same as the, clockwise versus counterclockwise order back in lecture 6. It's just a matter of personal taste. I find, though, that it does seem there's a bit of a consensus, or the majority of people that write about algorithms do seem to default to min heaps, and so fair enough, and I'm one of them. So I'm not just deferring to the majority, it just happens I also hold that opinion. But we'll use max heaps occasionally, including later in this lecture, we will talk about max heaps. Now, if you're interested, there are other types of heaps, and they do actually allow us to get better running times in many cases. So there actually are heaps out there that give us better running time than binary heaps on some operations, while maintaining the solid running time on other operations that we get with binary heaps. And we'll see, again, in, 10 or 15 lectures, a couple of cases where using one of those exotic heaps would allow us to improve an algorithm a little bit. But that's mostly presented as a curiosity. So I think just like sorting algorithms, if you look up heap on Wikipedia, it does have a great summary of different types of heaps, and it does compare them together. So we're only going to worry about binary heaps, but if you're interested, other types of heaps include Fibonacci heaps, which obviously sound really cool and mysterious, binomial heaps, which compared to Fibonacci heaps sound pretty dry and boring, and whatever a 2-3 heap is. We will actually talk about a 2-3 tree shortly, but we won't worry too much about 2-3 heaps. So we're going to only talk about binary heaps. Now, heaps are recursive structures, and this shouldn't surprise us, both because these are binary trees we're talking about and they're recursive, and because in our original idea with piles of numbers, we were thinking about applying this idea of dividing things in half recursively. So it makes sense we end up with a recursive structure. We have to be a little bit careful about how far we take this, but it is true, if you give me any heap, that is, if it meets the heap property and shape property at all nodes, then if I just ignore the root and I chop it up into 2 subtrees, each of those subtrees must also be a heap. And so that property applies. You can think of that as sort of a top-down property. If I take a heap and I break it into subtrees, the 2 subtrees will be heaps. However, and I'll come back to this later, it is not generally true that I'm allowed to take 2 heaps and join them together and that the result will be a heap. So let's try and come up with a simple example of that. Here's 2 heaps here. And suppose that both of these heaps meet the heap property. So I won't bother drawing elements for these 2 heaps or drawing the keys, but suppose these 2 things are heaps. It is not the case that I can just take them and join them together with a common root and end up with a heap. It's true that if I did that and the heap property applied at the root, then the heap property would apply everywhere in the result. However, notice that I have a gap here. So if I join 2 heaps together, the shape property may not necessarily be satisfied. So if I want to do that, I have to be very careful to justify how I'm doing it. In general, while I can break a valid heap up into subheaps, I can't necessarily compose a new heap just by jamming 2 other heaps together. So be careful about that. Although we don't find that we need to do this very often, especially in this lecture. It does come up as something we think about later on, but not now. So we'll do some comprehension questions. Is this tree a heap? Well, the way I would look at this is, it seems to me as if the shape property is very easy to assess by sight. Now, that's not because it's an easy property to test for algorithmically. It's because we draw our trees in a nice orderly representation that allows us to glance at them. And to me, this is a glaring omission. This node, this gap here, clearly isn't allowed in a complete binary tree. That means the shape property is not satisfied. Now, it happens to be the case, I actually haven't checked this, but the slide is telling me this, so I'll take my own word for it, that the heap property is satisfied. But of course, as long as I can find a violation of the shape property, it's just not a heap, and I'm done. The answer is no, it isn't a heap. So there's no point in checking the heap property, because the shape property is easier to check at a glance. Okay? Is this a heap? Well, at a glance, it does look like the shape property is satisfied. Okay, so that's one step done. And then I think, well, I guess we're in for an example here where the heap property isn't satisfied. So let's go look and make sure the heap property is satisfied at all nodes. It looks like for 2, okay, 2 is less than 9, 2 is less than 3, so the heap property is satisfied at 2. 9 is less than both 41 and 50, so the heap property is satisfied for 9. 3 is less than 4 and 5. 41 is less than 60 and 61. 50 is less than 70 and 99. 4 is less than 6 and 7, and 5 is less than 8. And of course, the heap property always applies at the leaves because they have no children. And so in fact, this is a heap. The shape property and heap property are both satisfied and hold everywhere. Okay? Wait, no, I've got one more remark to make on this example. Notice that this is just a curiosity, so there's nothing particularly unusual about this, but since we've seen it, let's point this out. Notice that in this heap, every single thing on the right is less than every single thing on the left. Even something way down at the lowest level of the right-hand subtree is less than the thing at the root of the left-hand subtree. But that's fine. Maybe that seems a bit weird, but once you get used to it, I don't think it is. It's an interesting curiosity, sort of a weird coincidence, but it's completely valid. The heap property doesn't make any comment on the relationships of nodes in two distinct disjoint subtrees. All it says is, when you're working from the top down, the key at each node must be less than or equal to the keys in both of its children. That's it. So this is a valid heap. Okay, back to our comprehension questions. Is this a heap? Okay, so I glance at it and I'm like, yes, the shape property seems to be satisfied, so I do seem to have a complete binary tree. So I'll just have to go through and look for violations of the heap property. Okay, so 10 is less than 19 and 23, 19 is less than 20 and 21, but then I have this. So 23 is not less than 22. Okay, so that means I have a violation of the heap property, and so I can say it's not a heap. There could be other violations, but I don't care. I've already found one violation, so it's not a heap. So the heap property is not satisfied. One instinct that I sort of want to encourage, but maybe you've caught on to this, is that the heap property is easy to check if I just check every node, and it's a much more local property. Compared to the shape property, which applies to the whole tree globally. If I go back to that tree where the shape property wasn't satisfied, it was sort of difficult. I could figure this out at a glance by looking at the whole thing, but if I just look at part of my tree, like if I'm standing at node 9 and looking at everything, it's not easy to assess that the shape property is violated there. I could detect a violation of the shape property in this case by looking at node 23, because it's invalid for a node to have no left child but to have a right child. But I could concoct a heap where the shape property was violated, where it wasn't as obvious. Let's see if I have an example to work from here. So what about this situation? So clearly the shape property is violated because I have a gap here. But notice how it's not obvious from any particular node that that's the case. I guess if I look at the entire subtree of 23 somehow, I could detect if there is, let's put 50 here, if there's no node there, but there is a node there, a shape property violation has occurred, but it's not obvious from the local point of view of node 24, because from the point of view of node 24, it does look as if everything is in order. So I think my instinct there is that the heap property is a lot easier to assess because I can do it locally. I can just look at every single node and its children immediately and then decide if the heap property holds. The shape property is a global condition, and it's a lot harder to assert that it holds. To me, what that's telling me is that it might be easier when I want to modify my heap to prioritize the shape property because it's a bit more delicate. It's a little bit harder to fix if it's broken versus the heap property where, hypothetically at least, if I told you, could you fix this heap? So keep all the elements in the heap, but move them around so that the heap property is satisfied. It's pretty obvious how I could fix it. I just have to swap 23 and 22. So it's a very local change to fix it. And so I think going forward, that's telling me that maybe what I want to do is prioritize the shape property and do anything I can to avoid breaking the shape property, even if it breaks the heap property, because I might be able to fix the heap property easily compared to the shape property. But we're not done our comprehension questions. Is this a heap? Okay, so let's see. The shape property is pretty clearly satisfied. We have a complete binary tree, and it looks like we've got the heap property at 6, at 10, and at 17. So yes, it is a heap. Okay, I think that's enough exercises of that sort. Hopefully it's clear by now how we methodically assess whether something is or is not a heap. So now the question is, how do we, the question is actually, we want to prove one result about heaps, a pretty important one. Before we can move on, I wanted to talk about heap modifications, because that was where my train of thought was going, but we're not there yet. I want to prove this theorem first. This is something that we sort of assume, we sort of take it for granted, and it's because of that I'd actually forgotten this proof is sitting in the slides, which is that we sort of could see earlier that the minimum key pretty much has to be in the root, because the heap property recursively sort of forces it to be. Because if the minimum key was anywhere else, there would have to be a heap property violation. However, it's one thing to believe that, but I suppose we do need to prove it given how important it is to what we're going to do with heaps. So we want to prove this theorem here. Notice how I am stating the theorem for a min heap, because of course the minimum key being in the root is a characteristic of min heaps only. The same proof pretty much would apply for max heaps. It just would involve flipping some inequalities pretty much, like we have to talk about max instead of min. From now on, I'm not even going to bother putting min in brackets. If I just say heap, I mean a min heap. Okay, so here's the theorem. Unsurprisingly, we're going to prove this theorem by induction. I've mentioned this many times before, but I'm always pleased to point it out again, that doing induction on the height of a tree is wonderful, because the base case is generally just height 0, which is a single node. Even if more, and there's only so much you can do with a single node, so it's very easy to prove stuff about it. And even if more base cases are needed, and in this case, I am choosing to add more base cases, h equals 1 is also a pretty easy thing to work with too, because there's only 2 possible trees with height 1. There's this one and there's this one. And so it's easy to talk about all possibilities for those 2 trees if we're proving for height 1. And then the inductive case tends to be very easy if I'm working with height, for the types of theorems where that trick is useful. Okay, so I'm going to use induction on the height of the heap. I actually have to add a second base case. The footnote does explain correctly why that is. I'll try and illustrate that as well. But my first base case is for h equals 0. So when h equals 0, the only possible heap is just one node. We'll call it v. And this has no descendants, so the heap property holds vacuously. Like there's no way that this couldn't be a heap because there are no children to be in the wrong order. Similarly, the shape property holds vacuously. Well, actually, not really vacuously. The shape property definitely holds though, because a tree of height 0 is just a full binary tree of height 0. So that's it. So we're done. Okay, so that basis case is good. Okay, now what about this other basis case? So let me think about this. Maybe the easiest thing to do would be to show you the induction step, and then I'll just work backwards and explain why I need a base case for h equals 1. I will explain the base case, but why I need it may not be obvious until later. Okay, so when h equals 1, I have only 2 cases. Either I have the root and one child over to the left, or I have both children. But in any event, I only have these 3 nodes. And the heap property itself, so if I'm talking about a heap of a particular height, I can assume the heap property does hold. The heap property doesn't apply to every node in the tree, just to a node and its 2 immediate children. But in the case where h equals 1, that's all I have. So if the heap property holds, it is reasonable to conclude that the root does contain a smaller key than either of the other 2 nodes, and therefore that the theorem holds. Okay, so that asserts my second base case. I will come back in a minute to explain why I think the second base case is necessary. Now my hypothesis is, suppose the theorem holds for all heaps of height up to some height h, where h is greater than or equal to 1. Now this is actually a strong hypothesis. I'm doing this because I want to take apart a tree of height h plus 1 in a minute, and I don't want to make assumptions about the heights of its subtrees. So I'm making sure that I'm stating that the hypothesis is that the theorem holds for any tree of height up to or including height h. All right, so the induction step is, let's consider a heap of height h plus 1. So there it is, and so it's got a root. We'll call the root v, so the root's v, but it has key k in it. And then it's going to have 2 subtrees. Now, observe that because h, if I look at my previous slide, in my hypothesis, h is greater than or equal to 1. That means h plus 1 has to be greater than or equal to 2 here. And that tells me a couple of things. So because the tree has height 2, and it's a complete binary tree, because it's a heap, so the shape property holds, that means the root has to actually have 2 children. It can't have one of its child slots vacant. There has to actually be two actual children of the root. And we'll just say that the keys of those children are KL and KR. And that both of those things are the root of their own subtree of some height. Okay, so what do we know about the heights of those subtrees? Well, if the height of the whole tree is h plus 1, then at least one of the left and right subtree has to have height h, but they don't both have to have height h necessarily. So it's true that because it's a complete binary tree, they have to have, like the left subtree definitely has to have height h, and the right subtree has to have height either h or h minus 1. It is possible to have a heap where like if you think about this example here. So on this heap, the left subtree has height, so the whole thing has height 2, the left subtree has height 1, and the right subtree has height 0. And so the right subtree in general can have a height that is 1 less than the height of the left subtree, just because of the way that the complete binary tree works. But it'll never be any less than that, so it won't be h minus 5 or something. It'll be either, the heights will either be h and h minus 1, or h and h. And I'm going to clean up my diagram a little bit here before going forward. Okay, so what else can I say? Well, what I have are the keys of the two children of the root are KL and KR, and so I'm up to this point in the proof. Now, the subtrees below the root, so both of these two subtrees are both heaps. So as I observed earlier, if you take a heap and you look at one of its subtrees, that must be a heap. And by the induction hypothesis, since this heap and both heaps have height at most h, then I can apply the hypothesis to them, which means, in the case of the tree on the left, KL is less than anything in the subtree on the left, and KL is less than anything in the subtree on the right. Okay, and then I know that because the heap property holds for the root and its immediate children, then K has to be, so I have these two things. K has to be less than or equal to KL, and K has to be less than or equal to KR. And because KL is less than or equal to everything on the left, everything left, and KR is less than or equal to everything on the right, well, then that tells me that K has to be less than or equal to everything in the heap. And so the theorem holds. So what I've shown is that if I take any heap, notice how there's no qualification here besides that its height is h plus 1. If I take any heap of height h plus 1, I can show that the root of that heap is less than, the key in the root is less than or equal to the keys anywhere else in the heap. And that means that the theorem holds for every heap of height h plus 1. And that's the end of my induction step, and therefore, by induction, the theorem holds for all heaps of height h greater than or equal to 0. Okay, so one loose end to tie up. What was I going on about with that second base case? And the issue is basically this. Notice how it made my induction step easier to be able to assume that at all times, the root always has two children. It never has only one. There is only one situation in a heap where the root has one child. Like there's a situation where the root has 0 children, that's the height 0 case. And if the heap has height 2 or greater, the root must have 2 children. There must actually be a non-trivial subtree both to the left and the right of the root. And it made the induction step a bit cleaner to be able to make that assumption. There is only one situation where the root only has one child, and it's in the case where h equals 1. If h equals 1, you could have a left child but no right child of the root, and that would have made it a bit messy to talk about the case where in my induction step say, well, let KR be the key in the right child if it exists. And that's a bit messy. So because I wanted to assume that the right child always existed, I chose to extract out the h equals 1 case, which is the only situation where the right child might not exist, and treat that one separately. You could write a completely valid proof without that situation happening. So you could just have the basis be h equals 0, but you'd have an induction step that needed some special cases. And I figured it's easier just to pull the special case out and deal with it separately. So that was my decision. Maybe it was a good idea, maybe it wasn't. I think it cleaned up the proof. But when you write a proof, that's one of the editorial decisions you have to make. Okay, here we go. This is the one I wanted 10 minutes ago. I want to talk about modifying my heap because we know that we're working with a data structure, a living thing that can be modified over time. And so the question is, how do I add new elements, and then how do I remove the minimum element if I want to do so? Remember that because the priority queue just has these 3 operations, insert, minimum, and remove min, it isn't really my problem to show how I could remove arbitrary elements. All I have to prove is that I can remove the minimum element and talk about the running time of that. There's a case later in this course where we do actually talk about what if I do want to remove or even modify elements in the middle of my heap. That's something distinct from the priority queue abstract data type though. So for today, we just care about insert and remove minimum. I hope that by now it's clear that the minimum operation, just getting the minimum element, is sort of obvious at this point. I just look at the root and tell you what it contains. So there's no need for pseudocode for that. Okay, so how do I insert the value 187? And I know that when I'm done, I'm going to have a complete binary tree where the heap property holds everywhere. So I actually know in advance what my tree will look like at a high level. I may not know what's in every node because I might have to move some stuff around, but I know that when I'm done, because I have to have a complete binary tree and I'm adding a new element, the tree will look like this. Because that's the complete binary tree with one more element always looks like this. So like I said earlier, it appears that the shape property is very delicate. It's hard to enforce it. If I break the shape property somehow, it seems like it's rather difficult to restore it in the arbitrary sense, because I can't even figure out if it's broken very easily. What that tells me is maybe I should prioritize making the minimum possible change to the shape of the tree such that I know the shape property holds, and then going out of my way never to rearrange nodes again during my insertion, so there's no way I violate the shape property. And I, of course, have to define an insertion operation that guarantees me that after any possible insertion, both the heap property and the shape property hold. Okay, so as I said a minute ago, the shape property is very hard to enforce. So it's probably better if I'm careful and I make my modification to the tree such that I guarantee the shape property won't be violated, and then go out of my way never to rearrange elements so I don't create any violations later. Whereas the heap property, as I saw earlier, seems to be relatively easy to check and to enforce at a local level. So the way I'll do insertion is I know what my tree is going to look like when I'm done. So I know I'm going to have a new node down here. I'll just stick my new key into the new node that I know I will have to create, and then not modify the structure of the tree again during the insertion. Instead, I will then see whether I have any heap property violations and then rectify them. Okay, so let's do the insertion of 187. So what I do is I just insert it at the bottom level in the next available position. Now, I'm going to be vague on how I figure out where that is. What I will say is if you represent the heap with a linked representation, so a bunch of node objects and pointers, you can actually find that by performing a traversal from the top of the tree all the way down to the bottom. However, we're going to see later that we typically don't represent heaps with linked representations. There's a more efficient representation that uses a sequence. And so we'll just wait until then to talk about exactly how I locate the next empty position in the tree. It'll turn out to be very easy when the time comes. So I find the next empty position and I stick in a new node containing the key with my new value. And then I take a look at whether the heap property has been violated. And you can hopefully see that by performing a modification down here, the heap property is local, so it can't be violated over here. Nothing over here is changed, and the heap property applied before, so it should still apply. Same thing over here. The only place the heap property can be violated is right next to where I performed the insertion, so I check there. And I look at the parent of the new node, and it contains 35, and 35 is less than 187, and so the heap property holds. And that means I can assume the heap property still holds up above 35 because nothing's changed, and the heap property is a property that applies to a node and its immediate children. So I'm actually done. My insertion is now over. I was lucky that I inserted something with a very large value. But I won't always be that lucky. For example, right now, insert the key 34 into the heap above. Okay, so I already know where I'm going to put it. I'm going to put it in the next available position, which is this one. So I just look at the next position on the last level of the tree, and I add a new node there. Okay, so there's step one. And then what I have to do is verify that there are no heap property violations. So I take a look at 34 and its parent, because the violations, I can sort of work my way upwards in the tree here. I don't really care about the relationship between 34 and its sibling. That doesn't make any difference to me. I care about whether the heap property applies at the parent of 34. Okay, so 35 is greater than 34, so I have a violation. All right, so I guess I could fix the violation by simply demoting 35 to the last level and bringing 34 up. Because 34 is smaller, the heap property already applied before the insertion, so that means 34 will also be smaller than any other children below the node that I swapped. And so that means that I should expect that after that swap, the heap property does hold for this subtree. Now I then have to check to see whether the heap property holds for the parent of the node I just modified, because as I said earlier, every time you modify a node, you are opening yourself up to violating the heap property. But I noticed that 14 is less than 34, so therefore there are no further violations. There can't be, because the heap property holds above 14, it already did, and it holds below 14 on the other side. I don't really care about that, and so that means I'm now done. Okay, so that actually was a pretty lucky insertion as well. What about this one? Insert the key 6 into this heap. Okay, so we get the idea by now. What I want to do is I want to go and add 6 to the next available position, and then I want to work my way back upwards and fix any heap property violations until I reach a point where there are no violations. Okay, so I add my node 6, there it is, and then I look for violations. 6 is less than 89, so I drop 89 down and bring 6 up. Okay, and now because I just modified this node, I need to check that the heap property is still satisfied for its parent. So I compare 6 and 15. Okay, and there's another violation, so I swap. And then I check above the 6, and I look at the parent, and it's 3. So 3 is less than 6, and that means I'm good. And so the insertion is now complete. And maybe, I think the pattern is pretty clear. I'm only walking upwards in my heap. And this is great. This is one property of trees that we love, is that if I'm only walking upwards or downwards, then the number of steps I take is going to be equal to the height of my tree. And if I'm careful, maybe I can ensure that the height of my tree is small compared to the number of nodes. Although there are cases where the height of my tree could be very close to the number of nodes itself, maybe I can guarantee that my tree is dense enough that the height is small, and therefore that the walk all the way up from the bottom doesn't take very long. Okay, one last insertion. Insert the key 1. Okay, so I know where I'm going to put it. We'll just let the slides take care of that. I put it at the bottom level, and then I check for violations. Okay, so 1 is less than 15, so I swap. 1 is less than 6, so I swap. 1 is less than 3, so I swap. And I realize there can't be any further violations because I'm at the root. There is no heap property to hold above the root, so I must be done. So my walk starts at the lowest level. It'll always start at the lowest level because that's where my new leaf is always inserted. And then it works its way up, in the worst case, all the way to the root, but it never goes back down. Okay, so what do we call this operation? This is the insertion operation, obviously, but what do we call the process of letting this new element percolate up the tree? Well, I guess we could use an analogy that's sort of like, hey, let's consider each node to be heavy or light based on its key. And we want lighter nodes to float to the surface. So, that's an interesting analogy. That's a bit whimsical, but okay. And so for whatever reason, I guess the widely adopted term for this operation is bubble up, which I guess has some analogy to something floating to the surface. Of course, that I'm a serious person, and therefore these whimsical names don't really appeal to me. However, I've gone and looked for a better thing to call this. I am serious. Like every time I've taught algorithms, I'm like, is there any other thing I could call this operation? There are other terms for it, but they're sort of worse. So there are people that call the operation of floating to the top swim. Oh, that's sort of clever. That's too cute. I'm not going to do that. We're not going to get taken seriously with that. Okay, so then there are these people that are so stodgy that they can't say bubble up, and all they can come up with is something incredibly dry and boring sounding like heap up. The heap up operation. Well, that certainly makes you sound very serious, almost too serious, so I can't do that either. Okay, so, by the Goldilocks principle, I suppose we're just going to call it bubble up. Fair enough, I tried. Okay, so we'll call this operation bubble up. We're stuck with that. That means people will think that what we're doing is a joke. Fair enough, it's definitely serious from our point of view. We're working with trees, and trees are a big deal. Here is a recursive implementation of my bubble up operation. Now, the insertion itself has more steps than this. I'll come back to that in a minute. But the actual restoration of the heap property is done by this. And so the way it works is, so I'm going to use object-oriented notation here, node.parent. I'm going to assume that the key and the parent are properties of the node object. We're going to assume, as we have before, that the value of parent for the root is some invalid symbol like this. So the analogy of a null pointer. So this is the case where I'm actually at the root. If you give me a node and say bubble up from here, and I'm already at the root, well then I'm done. There can't be a violation of the heap property above the root. If I'm not at the root, then I ask, is the parent's key greater than the key in this node? So that would be a situation like this. If the node that I'm looking at has a smaller key than its parent, well, then I have to do a swap. And so the swap itself is constant time. All I do is just pick up the item in each node and put them back in the opposite order. And then I recursively call the bubble up function on the parent so that it can propagate the new value further up the tree if needed. So there's the recursive implementation, and here's an iterative implementation. And you will see that unlike a few other examples of recursive versus iteratives, like there are certain functions like adding elements to a list where the recursive version is just beautiful and the iterative one is a bit of a pain. In this case, they are essentially identical to the point that because this is tail recursion, the recursive call happens at the last line, odds are if you compile this, if you wrote this in C++ or in a compiled language, the compiler would probably convert this recursive one to this iterative operation at compile time. Like they are that close, they're that similar in function. So as far as which one do you write if you're implementing a heap, just do whichever one makes sense to you. It's a matter of personal taste. Don't feel judged by others because you choose iteration over recursion. Just write the one that makes sense. So they're both pretty much exactly the same. But in both cases, I hope it's clear that the bubble up operation walks upwards in the tree, and therefore that the running time has to be proportional to the height of the tree. Because other than walking upwards, that would be moving from a node to its parent, all I'm doing is constant time stuff, a bunch of comparisons, swapping things, and that's true whether I use the recursive version or the iterative version. So what I'm doing in the worst case here, if the new key I'm inserting is less than everything else, it becomes the new root, which means the bubble up traverses a path from a leaf, my new leaf node, all the way to the root. In the best case, bubble up, so best case would be like my first insertion of 187 where I had, 35 or something, and I add the value 187 and I'm immediately done. My new leaf is already in the correct position. That's the best case. The worst case, I get all the way back up to the root, and that would be big theta of h operations, because everything else besides walking upwards is constant time. So we can see that it looks like the efficiency of our method is going to come down to proving that h is a small number. Now, the insertion itself is pretty straightforward. I just add the new node, and then I perform a bubble up starting at that node. As I said earlier, I'm going to leave this a bit vague for now because I need a bit more stuff before it's clear how we'd want to do that. But certainly, even in the worst case, even if you're using a linked-based heap, it is possible to figure out where the next position on the last level is and add a new node there in big O of h operations. We'll see later there's actually a way of doing it in constant time. So that's why I'm leaving this vague. So certainly, in any event, the entire insertion takes big theta of h time. Now, what about removal? So remove the minimum key, which is the value currently in the root, from the heap above. And so I guess just like insertion, we sort of know our priorities here. What we know is that when we're done, we have to have the heap property and shape property holding everywhere. But also that we've already seen it seems to be possible to fix heap property violations with a relatively methodical procedure. Now, this might require different modifications, but it seems like we should hold out hope that that should work here as well. Whereas the shape property seems to be a bit more ornery and a bit harder to restore if we break it. So we should prioritize maintaining the shape property. What do we know about the shape of the tree when we're done? Okay, so when we're done, this node will be gone. Well, we don't just want to delete it because then we end up disconnecting the tree. Okay, so what we'll do is this. We'll just take out the number 1 and put it off to the side. That's going to be our return value from RemoveMin, the number 1. Okay, so then we say, well, when we're done, we're going to have a tree that has 1 fewer nodes in it. And because it's a complete binary tree, we actually know to begin with that the tree will look sort of like this when we're done. This position will be missing. But we don't want to delete the node 15 because obviously the key 15 is still part of my collection. Okay, so how about this? Here's an idea. I've already removed something from the root. The root is sort of empty at this point. And I have this value 15 over in a leaf that I would just as soon get rid of. So how about this? We'll take the value 1 out of the root and put it over here to the side. We'll then take the number 15 out of the last leaf on the last level and just put it up in the root for safekeeping. And then we can delete this node of the tree. So our tree now looks like it's supposed to look when we're done, although there may be heap property violations. Okay, so I'll call that step 1. Step 1A is grab the key that's in the last leaf and just put it in the root. That way we're not losing it. And then step 1B is, so now this leaf contains nothing. It's sort of an invalid leaf or a degenerate leaf. Now I can just get rid of it. It contains nothing useful. Okay, so step 1B, just get rid of that leaf. So now I have a tree that looks like what I want, except that the heap property may be violated. Okay, so where would the violation be? Well, the only two modifications I've made are here and down here. But down here, I just deleted something. So that's not going to create a heap property violation. That's not going to make the key 6 greater than any of its children. So obviously, the violations I should look for start up at the top. And I suppose if we think about it, the number 15 shouldn't be this high in the tree. It should be somewhere further down. And it makes sense, I guess, that what we're going to do is sort of the opposite of an insertion. We're going to work our way down the tree and try and move this key back to where it belongs. Okay, and so unsurprisingly, the operation we're going to do is going to be called bubble down. Now, for the people that use the sort of cute names and call it swim for bubble up, they would call it the other operation sink. So sink and swim. So that's very clever. It's too clever for my taste, though. I'm not going to call it that. Okay, so we're going to call this bubble down. All right, so we take a look at the root, and in each step, we've just modified a node, so we investigate the nodes surrounding it to ask whether there's a violation. It's clear in this case we have to be looking at the nodes below it, because we're already at the root, and there's nothing above it. So I ask, is 15 less than both of its children? And really, it'll become sort of clear pretty quickly. We only really care about the smaller of the two children, because if 15 is greater than the smaller of the two children, then it's definitely greater than both of the two children. And so that's the if 15 is, if the smaller of the two children is less than 15, then I should move the smaller child up. It doesn't matter what the relationship of 15 is to the other child. So I got that a bit backwards. Because we know that if the smaller child gets moved up, since it was the smaller of the two children, it will always be less than the larger of the two children. So all we really care about is comparing the key that we're working with the key that is the smaller among the the children of that node. Okay, so clearly there's a violation because 15 is greater than 3. So what I could do is just swap 15 and 3. Because 3 is the smaller of the two children, moving it up will not violate the heap property with respect to the other child. So I make this swap. This resulted in a modification happening to this position. I no longer care about anything happening over here because nothing was modified over here. The heap property already held at this node and below it, and with my new 3 as the root, the heap property holds with the 3 with respect to the 14. However, maybe there's still a violation where I just put the 15. And so I look at the children of the node 15. I notice that 15 is greater than the smaller of its two children. It's true that it actually is less than the larger of the two, but I don't care. I mean, it's certainly, the heap property is not satisfied. Because 6 is the smaller of the two children, it won't harm anything to move it up, because 79 will obviously be greater than 6, because 79 was the larger of the two children. Okay, so I swap again, and you can see we're now doing swaps going down the tree. Although this operation is a bit more labor-intensive, because at each step we're comparing the key of a node to both children, versus the bubble up case where we just look at the thing one above it, the parent. All right, and at this point I notice that 15 is in the right position. The heap property is now satisfied, and so the removal is now complete. Let's try removing the root of this heap. So I want to remove the value 4. Okay, so I put the value 4 aside, and then I move the key 99 into the root for safekeeping, which allows me to delete the node that contained the 99. Okay, so that's step 1A is to move it, and then I delete it. All right, and now I have to perform the bubble down operation. So I ask the question, is 99 greater than, or is the smallest of its two children less than 99? And the answer is yes. I don't even care about the other one, although it's true that 99 is greater than 91. I only care about the smaller of the two children, and so I perform this swap. I move 7 up and 99 down. And I ask the question again, is the smaller of its two children less than 99? And the answer is again yes, and so I move the 9 up and the 99 down, and then I ask it again, and I swap it with the 10. And of course, once I hit a leaf, I have to be done. There's no way I could go further down than that. And at this point, the heap property always holds. As we know, if the node has no children, the heap property vacuously applies. So in this case, the removal is complete. Here's some pseudocode for my bubble down operation. So here, the base case, this is the recursive version. You give me a node to bubble down. If it's a leaf, then we're good. I'm done. Otherwise, and for the sake of making this easier to glance at, I've cleaned this up a bit. There is a bit of tedious work to be done in line number 5. It's all constant time, but there is more. I can't just say, give me the smallest child. I mean, there is more to it than that, but it's just if statements. So the reason why I didn't write it out fully is because it's got a bunch of annoying cases. And the cases are basically, what if you have a left child but no right child versus what if you have both children? If you only have a left child, well then your smallest child is the left child. If you have two children, then you compare their two keys together and choose which one is the smallest. And so you know how to do that. There's no need to write that out in full. That's all constant time. I'm just looking at the two children positions and then comparing their keys if necessary. So let smallest child be the node object for the smallest child. And then I want to ask, is the key of the node I'm looking at greater than the key in my smallest child? If the answer is yes, then I have to actually swap values. So that would be a situation like this. So if I've got this situation here, the smallest child contains the number 6, and if we discover that the 10 is greater than 6, well, that means we have to do a swap. So we move the 6 up and we move the 10 down. And then once we're done with the swap, we call bubble down on the child. So I've swapped keys, which means that the smallest child node is still in the same position, but now has a new key. And so I perform bubble down to propagate the key further if needed. There's the recursive version. Here's the iterative version. They are both effectively identical, so write whichever one makes sense to you. And in both cases, hopefully we can show, or hopefully it's clear, because I don't intend to write a proof of this aspect, hopefully it's clear that this is also a big theta of h operation, because what we're doing at each step is walking one step down the tree in the worst case, and everything else we're doing is constant time. So figuring out which child is the smallest, that's constant time. The if statement, the swap, that's all constant time as well. And in the worst case, we don't hit this break statement until we're actually at a leaf. We only end the loop because the condition is violated. So we also end up with a big theta of h operation, so the height of the tree. So of course, we have a lot invested in being able to show that the tree has a relatively small height. Here is the full RemoveMin operation. So I find the root. I also go figure out where the rightmost leaf is on the last level, and then I grab the key from the root for safekeeping. I then move the key from the leaf I'm going to remove, into the root. I then delete the leaf, then I perform the bubble down, and finally I return that minimum key that I put aside earlier. Because everything else was constant, except maybe for this, which is big O of h in the worst case, if you're using a linked structure. And I know I haven't talked about that in greater detail yet, because we're going to discover it is actually constant for our most common use case. That means this whole thing is just big theta of h. Everything's constant besides maybe this, which is h, and then this is also h, and so it's all big theta of h. So I guess what we need to do is to assert that the height of a heap is guaranteed to be relatively small. We know that in general, if I'm talking about a binary tree, so let's consider a binary tree with n nodes. Here it is. Here's a valid binary tree with 5 nodes. It has height 4. And in general, if you give me n nodes, I could make you a binary tree with height n minus 1. That's bad news, because that means if our algorithms are going to have running time h, that means it actually takes, that h could be n, so we have big theta of n. So what I need to show is that h on a heap is guaranteed to be significantly smaller than n if I want to get that asymptotic improvement over linear time that we started out looking for. And we can do that, and that's what the shape property is for. By forcing the heap to be a complete binary tree, it is forcing the heap to be sort of densely populated. In this situation here, every level of this tree is pretty sparse. There's very few things on each level. And even if I fill in the level a little bit, but don't make it a complete tree, so in this case, the height would be about n over 2, which is still linear in n. What I want is to guarantee that the height is, frankly, I want it to be log n. I want it to be something significantly less than n. And we can do that with a complete binary tree. And I want to prove this theorem. So actually, I want to prove 2 theorems. This theorem is the ultimate result I want, which is that h is big theta of log n, so that our bubble up and bubble down operations are indeed big theta of log n. To do it, I'm actually going to prove 2 theorems, one of which seems like the opposite of what I need. So anyway, a heap of height h is a complete binary tree, and we already know from a previous lecture that a complete binary tree of height h with n nodes has this situation going on. And I guess this isn't a separate theorem. This is a theorem we already proved, but bringing it in, it doesn't look like this is exactly what we need, but this is a case of simply, if we manipulate this inequality the right way, we can get exactly what we want pretty easily. So if I have a heap of height h, it has to be a complete binary tree. We already know that the number of nodes is bounded between 2 to the h and 2 to the h plus 1, all minus 1. All we really need to do to show that the height is less than or equal to log n is take the logarithm of each part of this inequality. So we start with our theorem from, 2 lectures ago, and then we just take the logarithm of everything, and we get that h is less than or equal to log base 2 of n, which happens to be less than or equal to this, but we don't really care as much about that. All we care about is that gives us big theta for free. Or this part gives us big O, and then this part gives us big theta. or big omega, which then gives us big theta. That's enough to assert that h is big theta of log n, and therefore that my algorithms that do bubble up and bubble down are actually big theta of h, which is big theta of log n. And so we can now go slot heap in among our other candidates for priority queue. And notice that we have an insert operation that, because we know that h is big theta of log n, insert is big theta of log n, and remove min is big theta of log n in the worst case. And there's a whole bunch of results we can pull out of this. What I want to do is go back and spend a bit more time talking about heap representation, but it's certainly true that we now know enough to sort of understand, if I talk about the algorithm heap sort, where I'll be going with it. Because all I need to do to sort things with a heap is do a bunch of insertions followed by a bunch of removals. But we'll come back to that later. One thing I want to observe is that if we implement our heap using a typical linked representation, so we've got a bunch of node objects that are connected to their children and to their parent via pointers, that there's going to be a lot of overhead, and that we may not need the full flexibility of that operation. That is, once a node is in position, we might swap keys around, but we never reconfigure the pointers. We never rearrange the nodes in the tree. So having a bunch of pointers that we follow might not be necessary. It might be a little bit wasteful in terms of constant time things, like the amount of time it takes to follow pointers. We already know that traversing a linked list, although traversing every element of a linked list is linear time, as is traversing every element of an array, there is a lot of overhead in practice with iterating through a list. And that's one reason to try and consider some alternative representation like an array. And the same is true of a heap. Although there are lots of cases where your binary tree does need to be represented with a linked representation, the heap turns out not to be one of them. Because we know that a linked data structure has high overhead compared to things like arrays, which are contiguous sequences. That itself isn't enough, but it also turns out that there is a clever way of representing a heap in an array that gives us a pretty good efficiency, because representing trees inside of an array could be inefficient in certain cases. So because the heap is dense and has a very low height, those are the key things we require. There is actually an array-based representation which gives you the same efficiency of the heap operations. You can still traverse the tree very quickly, but also you get the low overhead of being able to traverse arrays. So doing quick indexing and the array being a big contiguous block so that it optimizes things like cache performance. And that's worth it not only because it does result in a speed up, like a constant time speed up, but also because it turns out it helps us solve one of our issues, which is how do I easily find the last leaf on the last level? So before I get to that, let's do a thought experiment. Here is a heap. I want to do a level order traversal of this heap. And remember that any level order traversal, which is a form of breadth first traversal, our typical level order traversal visits every node in level I before any node on level I plus 1. And nodes are visited in left to right order across each level. So if I do that, I should expect to see 3, then 14, then 15. So that would be level 0. That would be all of level 1. Then 32, then 38, then 35, then 89, there's level 2, followed by 92, 79, and 65. So, whoops, 65. So in other words, I'm going from left to right, top to bottom. And I've written this out in a much less sloppy way on the slide. There it is. There is our level order traversal. Now, I want to number my nodes based on where they appear in my traversal. So, of course, I saw 3 first, then 14, then 15. I'm going to start my numbering at 1 because I'm just numbering where things, like when I saw something. I saw 3 first. And then I saw 32, and then I saw 38. Okay, so you get the idea. I'll switch to the typeset numbering. There we go. And now I want to observe that a very interesting pattern is apparent here. So let's take a look at the node that I've numbered, node 5. What is the index of its left child? Oh, it happens to be 10. Oh, that's neat. So 2 times 5. Well, what a weird coincidence. What about this node, node 3? What is the index of its left child? Oh, it's 6. So 3 times 2. Weird. Node 1, 2. So 1 times 2. What about node 8? Well, or what about node 4? 8, which is 4 times 2. That's weird. Okay, what about the parent of each node? What is the parent of node 5? Okay, well, it's 2. But that's like 5 over 2 with integer division. I just truncate it down to an integer. Okay, what about 4? Well, 4 divided by 2 is 2. Interesting. What about 10? 10 divided by 2 is 5. What about the parent of 7? Well, 7 divided by 2 is 3.5, but truncating that down, it comes out to be 3. Interesting. There's an interesting pattern of these indices that seems to correspond very easily and conveniently to the parent-child relationships. And then finally, what about right children? Okay, so the right child of 2 is number 5. Okay, well, that's not quite 2 times 2. It's 2 times 2 plus 1. Weird. Okay, the right child of 4 is 9. 4 times 2 plus 1. The right child of 1 is 3. 1 times 2 plus 1. The right child of 15, or of 3, is 7, which is 3 times 2 plus 1. So actually, it does look as if there is a set of predictable numerical relationships between this indexing scheme that I've come up with and the parent-child relationships in the tree. In a sense, what that's telling me is I don't need to bother making a pointer to nodes. If I know the index of each node, I could just use basic arithmetic to figure out what the children and parents of that node are. So my observation is, if a node has index I in this numbering scheme, where I number the root with a 1, and then I just go across each level from left to right with subsequent numbers, the parent of that node has index I over 2, or the floor of I over 2, because I over 2 might not be an integer, and the children have indices 2i for the left child and 2i plus 1 for the right child. And since it's a complete tree, which is to say, since every level is completely full, the indices are contiguous, and the maximum index, if I look at a tree containing n nodes, is equal to n. So there are 10 nodes in this tree, and sure enough, the last index I assign is index n, index 10. So here's an idea. Instead of representing the tree with a bunch of objects, I could just jam all of these keys into an array, and I just use the index of the array to tell me which node I'm talking about. So in other words, the thing that appears at index 5 of my array, I will interpret that to be the key stored in the node with number 5. And what's really interesting about this is, as I said, because the last index used will equal the number of nodes, my array will be densely packed. I won't have any wasted space in the middle of the array. So I end up with this. If I choose to represent a heap with this representation, it's useful to add a bunch of empty space to the end of the array to accommodate if I want to add some new nodes later. And of course, if I fill up that empty space, it could take some time to resize the array should I want to add even more nodes after that. So with this representation, this more implicit way of representing nodes, if I want to know the parent of node I, then I just evaluate I over 2 and take the floor. The left child is 2 times I, the right child is 2 times I plus 1. All of these things I can compute implicitly. There's no need for pointers or objects to do this. Now, you might be wondering, why can't I just do this with every binary tree I've ever seen? I mean, if there's this convenient way, and I know that linked representations are slower, why don't I always use this? Well, let's think about that. Let's make a tree with, let's do these 5 nodes here. Okay, so I've got 5 nodes. The index of my root is 1. The index of the right child of the root is 3, then 7, then 15, and then 31. Okay, this is a bit nasty though, because I have a tree. If I store this tree, this sparse tree, in an array, then I have to have an array of size 31. But I only have 5 elements. And if we extrapolate this a bit, you might observe over time that if I have n elements and they all lean to the right, then what I'll end up with is the last index will be 2 to the n minus 1, which means to store only n elements, I need an array of size big theta of 2 to the n. Yikes! So as a result, although I actually can store any tree that I want in this array-based representation, unless I can guarantee that the height of the tree is small, I might end up creating a massive array full of empty space, because most of the indices of this array are going to be empty. They're going to refer to nodes that don't actually exist. And so the array-based representation is possible, but not practical for cases where my tree is sparse, where it's not guaranteed to be very densely packed. Because I know that the height of my tree is big theta of log n, or I guess more generally, the size of the array I have to create is going to be big theta of 2 to the h. And if h is close to n, then it's going to be big theta of 2 to the n. But because I know that h is log n, well, 2 to the log base 2 of n is just going to be n, which means the array I create is just going to be big theta of n. So that's why the array-based tree representation is really good for this application, but may not work in general for other tree-based applications. There are other cases where it would be useful, but it doesn't work for storing arbitrary trees that could be more sparse. Another thing I want to observe is you'll notice what I've done here is I'm using an array-based representation, but the first index of my array is index 1. So maybe we're all used to indexing at 0. And I don't know, it tends to be the case that once you've learned languages that like 0-based indexing, you become very attached to the concept. You think the idea of indexing starting at 1 is sort of weird or degenerate or something. Remember that that is an arbitrary choice of ours. The reason why most languages we use today index starting at 0 is because a lot of languages in the past that were very influential. So for example, the C language indexed arrays starting at 0. The reason why C indexes arrays starting at 0 is actually well justified because C is representing arrays using a very low-level model of the memory, using essentially pointer arithmetic, and that makes sense to use 0-based indexing. But there's no reason why indices have to start at 0. And I should add, languages like Java and C++ are C descendants, and so they continue that tradition. Even languages like JavaScript, and I mean, who even knows what JavaScript is based on? JavaScript is a distant descendant of C by one branch of the family. And so a lot of modern languages have inherited C's and other similar languages 0-based indexing. But there's no reason arrays have to be indexed starting at 0. So I could point out that Fortran uses, or traditionally used 1-based indexing. That wouldn't help prove my point at all. Saying that Fortran did something is often an argument against doing that thing. Modern Fortran, if you believe such a thing exists, actually allows you to decide how you want to index the array when you create the array. You can choose to index the array starting at 5 if you want to. And there are languages like MATLAB that index arrays starting at 1 or allow you the option of doing that. There's nothing inherently wrong with that. It is, however, true that we need to use 1-based indexing for this application. If I number the root 0, then everything breaks down because, 2 times 0 is 0. So I'm not going to end up getting this nice relationship where the left child is at index 2 times I. So the best way of doing that, I think, is numbering starting at 1. How do you achieve that in practice? Well, there are two options. One option is to use a 0-based indexing scheme and just every time you do indexing, make a little adjustment. So you pretend you're indexing with 1-based indexing and just subtract 1 from the index before you go to the array. You could do that. Fair enough. I don't think that's a good idea. What I would always do when I make a heap is this. I want an array that has 12 positions for elements. So I make a 0-based array that starts at index 0 and has size 13. And then I just pretend that index 0 isn't there. I allow that space to be wasted. It doesn't hurt anything for me to waste one slot in my computer's memory. It's got tons of memory. It's way easier to preserve the elegance of my problem to just waste a position of my array. And that's what I do. If I'm using a language like C, I could also use weird pointer shenanigans to achieve the same effect while apparently not wasting the space, although that's a Pyrrhic victory because I'd waste just as much space with the pointer shenanigans as I would by the trick that I just described. So for me, when I make a heap, I just create, or an array-based heap, I just create an array that's one element larger and then pretend there is no element, no index 0 of the array. Now, this tends to lead to more streamlined performance because arrays are very efficient in a constant time sense because the computer has a much easier time working with contiguous blocks of data and indices versus following pointers all over memory. And in the case of a heap, because I don't need to rewire the ordering of nodes, that is, once a node is at index 2, it's going to be there forever. Even if I might swap around the values inside the node stays in the same position. So I can just have this fixed static structure of my tree persist forever and just use the indexing scheme to do my parent and child traversals. And one other really wonderful benefit of using an array is that figuring out where to perform my insertion or removal is absolutely trivial. So the question is, suppose I want to do an insertion. Where is the next leaf in the tree going to be? Well, I mean, it's going to be here. Okay, fine. But what index is that going to be? Well, it'll be index 11. It'll be the next vacant index of my array, which means all I have to do to locate where to put my new elements when I insert them is keep track of the current size of my array, which is 10 in this case, and just say, well, the next index up, that will be my new leaf. And then when I go to add it, that's actually a constant time addition. I know in advance where that index is going to be. All I do is go there and stick my new value in. So I think we have an example of some insertions to show that off. Yeah, there it is. So insert the key 10 into this heap. All right, I go to index 11, the first vacant index of my array, and I add the key 10, okay? And then I perform the typical bubble up procedure using the indices as a way of determining parent-child relationships. So I compare the value in index 10 with the value in its parent, or index 11. The parent of index 11 would be index 5. 11 divided by 2, take the floor. And of course, we can see that on the diagram as well. So I perform the comparison. We see that I violate the heap property, and so I perform a swap. Okay, I check for further violations. The parent of index 5 is index 2. Okay, so I take a look at that. I have another heap property violation. I perform a swap. And then I check for more violations, but in this case, I'm actually done. So it turns out that there is no violation above 10. The parent of node 2 is 2 divided by 2 equals 1. And so I was able to do all of this traversal without the need to follow any pointers or use a node object. All I'm doing is performing arithmetic on an index. All right, what about removing the minimum? Okay, so step 1A of my removal is I put aside the minimum value 3, and then I take the value in the last leaf and just put it in the root for safekeeping. There we go. That's step 1A. So that means that I have now an element in my array that's no longer used. And instead of deleting the node, all I really have to do is, if I'm keeping track of the size of my heap, if the size is currently equal to 11, I just decrement that. And now I know this node doesn't really exist, so I can't use it. And if I were bubbling down or something, I take into account the size when I decide whether a node is real or not, whether it actually exists at the moment. Okay, so then step 1B is delete the leaf. But deleting the leaf is basically just pretend that index 11 is no longer there. So you're no longer using it as part of your tree. And now I perform the bubble down operation. So I look at the two children of node 1. That would be, so 1 times 2 is 2. 1 times 2 plus 1 is 3. I look at both of them. The smallest child is 10. 10 is less than 38, so I swap. Now I look at the two children of the node that contains 38, which is node 2. The two children are 2 times 2 is 4. 2 times 4 plus 1 is 5. And I notice that 14 is less than 38, so I swap. I now look at well, there aren't two children of the node with index 5. How do I know that? Well, let's take a look at the two. So I know that the current size of my heap is 10. Okay, so the two children are, so 5 times 2 equals 10, and 5 times 2 plus 1 equals 11. But since 11 is greater than my current size, I know that this isn't actually a real node. There is no right child. And my bubble down operation can just have an if statement to check for this. So the only node I have to look at is node 10. And I see that 38 is less than 65, and so my removal is complete. And so hopefully that's enough evidence that you can, in fact, replace the entire tree traversal mechanism with simply working with indices and use them as an implicit representation of the parent-child relationships in the tree. Okay, there's one thing to observe. And now I want to talk about what if I want to make a heap all at once out of a sequence of keys. Now we know that for the priority queue data structure, we have to allow the possibility that insertions can happen sporadically. So I could do a few insertions, I could insert these elements, then do a RemoveMin, then insert a couple more elements, then a RemoveMin, then insert all these elements, then and so on. But I should also consider, what if I happen to have a huge sequence of keys and I want to make all of them into a heap from nothing all at once? So not only am I doing a bunch of insertions in a row, I'm starting from an empty heap and doing a bunch of insertions. How do I do this? Okay, well, I mean, the easiest way would be to just perform n insert operations starting with an empty heap. Fair enough, I can obviously do that. The question is, I guess, how long does that take? So each insert operation, if the heap already has size n, each insert operation takes log n time, which means the sequence of n insert operations has to take at most n log n time. But does it take n log n time? And the reason I ask is because if I think about performing n insertion operations on an empty heap, that's a bit different than performing n insert operations on this heap. If I perform an insertion on this heap, it is reasonable that it could take log n time, because I could start at a leaf and go all the way back up to the root, which the height of the tree being log n would take log n time. But if I'm performing a bunch of insertions starting from nothing, isn't it true that some of the insertions happen when the heap is tiny? I mean, the insertion of the first thing has to be easy. That can't take log n time. I don't have n things to work with yet. I don't even have n over 2 things. So it makes sense that some of my insertions, if I'm inserting an entire sequence at once, do not need to take log n time. And the question is, if I'm doing n of them, is it possible that I can do all of the insertions in a total time that is less than n log n? And the answer is, from an asymptotic point of view, actually no. So the question is, what is the true running time of a sequence of n consecutive insert operations with no remove minimums on an initially empty heap? And the answer is, it actually is n log n, because we can show that big omega of n log n operations are needed in the worst case. But it's not a trivial analysis. We actually do have to make some kind of an argument to show that this is the case. And here it is. So it's not a full, I don't need an induction proof. I just have to basically observe that if I consider a sequence of insertions, let's say into this heap, then most of the insertions happen when the heap is already pretty tall. So it's true that there are some insertions that happen when the heap is only this big, and it's true that those insertions probably don't take log n time. But notice that because of the way binary trees are, the heap is sort of bottom heavy. Most elements in the heap at any given time are near the bottom of the heap. And if I think about doing a bunch of insertions, suppose I've done n over 2 insertions. By the time I've done n over 2 insertions, I probably already have a heap of about this height. So at least half of the insertions that I do are into a heap that is of height at least log of n minus 1. So that would be log of n over 2. And that's the observation I'm trying to formalize here. So the observation is, in a complete binary tree of height h greater than 2, and actually this is overly cautious. It turns out I could prove this for h is greater than or equal to 0. But for the sake of making the arithmetic easier to justify, I'll just say h greater than or equal to 2. At least half of the nodes of the tree are in the last 2 levels. So if I consider a complete binary tree in a sort of abstract sense, okay, that's like a full binary tree. Maybe there's like a notch taken out of it if it's a complete binary tree. What I want to argue is, if this has height h, then if I look at the last full level, that would be level h minus 1. And if I look at every level above that, so that would be h minus 2 levels, all I'm going to argue is that half of all elements of the heap, half of all the nodes in the heap, are at level h minus 1 or below it. And actually, I can pretty much show that if I ignore the elements at level h, half of all the elements above level h are at level h minus 1. And the reason why that's a useful argument is what it's telling me is that when I get to inserting the second half of my sequence of n elements, the tree will already have height pretty much log n. And that means that the insertions will all take log n time. So the second half of my sequence, so n over 2 insertions, require at least this number, this amount of time. So I do n over 2 insertions, each of which requires log of n over 2 time. And that's going to be log of n all minus 1. And so that's big theta of log n, which means if I perform n insertions, unfortunately the running time will still be at least some constant multiple of n log n time. Okay, so the basic logic behind the proof is if I consider a complete binary tree with height h, then up until level h minus 1, the tree is full. Every level contains the maximum number of nodes up until and including level h minus 1. And that means that there are 2 to the I nodes on level I, up until I equals h minus 1. On level h, there's at least 1 node on level h because the tree has height h, so there has to be something down there, and at most 2 to the h nodes. And the claim is basically, even if I ignore level h, that half of the nodes above level h are on level h minus 1. So the claim will just be half of the nodes of the tree are at level h minus 1 or level h. And this is true of all complete binary trees, heaps or not. And all I need to do for the proof is talk about levels 0 through h minus 2 up until level h and then level h minus 1 on its own. So if I look at everything up to level h minus 2, well, that's going to be a full binary tree. And we know that a full binary tree of height h minus 2 has this number of nodes in it. So in general, if I have a full binary tree of height k, the number of nodes is 2 to the k plus 1, all minus 1. And so applying that to h minus 2 gives me this. Okay, the number of nodes on level h minus 1, as I said above, is 2 to the h minus 1, which means the number of nodes above level h minus 1 is this number, and the number of nodes on level h minus 1 is this number. And so that means that more than half of the nodes are at level h minus 1 or below, because there are more nodes at h minus 1 than above it, and there are even more nodes below h minus 1. There's somewhere between 1 up to 2 to the h nodes below it. So that means half of the nodes of the tree are at or below level h minus 1, which means that my insertions, by the time I get to half of the insertions done, all of the remaining insertions are being performed on a tree whose height is more or less log n. And that means that I'm going to end up doing big theta of n over 2 times log n operations, which is just big theta of n log n. So if I want to perform n insertions into an empty heap, it is n log n running time to do so. Can I do better, though? Is there a better way, if I have all of my keys in advance, to build a heap out of that entire sequence of keys and end up with a running time faster than n log n? And the answer does turn out to be yes. And to be honest, I actually was sort of astonished by this when I first saw it. I still think this is a really cool algorithm. This is actually a really interesting example of the way that our analysis techniques can sort of maybe they betray certain details. There are certain things that we can't notice just by looking at analysis, but that if we know how to do something, we can find that applying the same analysis techniques, like there's actually a surprising amount of flexibility in the amount of time that things take. And the idea is essentially, I guess, at a high level, what we're doing if we perform n insertions is a sort of top-down construction. The heap grows from the root and then down to the lower levels. What if we do it in the opposite order, is basically my question. And I'll come back to that in a minute, but I want to illustrate one other property first. Here are two heaps. For the sake of the example, this is mostly a thought experiment. Both of these heaps are full binary trees. What I want to consider is this. Suppose I take some random number, so any number I want, and I create a new node containing it. So I mean, it could be 100, or it could be 0, who knows, and I just attach it to form a new root. In other words, I join these two heaps together with a new root. Now, I mentioned earlier that this is a thought experiment. I can't generally do this because I can't be guaranteed that both things are complete binary trees. But for this example, I'm allowed to do it. So suppose I join them with some new root. In this case, I actually chose the value 8. The question is, how quickly can I restore the heap property? Well, the answer is, of course, because I have heaps on both sides, this is basically the same as a RemoveMin operation. I'm just doing a bubble down. Okay, so what I could do is run a single bubble down operation to move the new root key 8 down to where it's supposed to be. And that would take big theta of h time. Okay, that's an interesting observation. Okay, so as I said a minute ago, in general, if you want to merge two heaps, more work might be required than was required in this example. Because if I take two arbitrary heaps, the one on the left has to be a full binary tree for this merge to work, and that may not be true in general. Okay, so just be aware of that. There's an important disclaimer. Okay, so let's try the same task again, but I'm going to sort of invert the order of operations a bit here. I'm going to not think about it in terms of constructing a heap one node at a time. I'm going to think about it sort of as a meta version of our logic for insert and remove. Suppose I try to insert all elements at once and then repair the heap property globally. So I basically make everything into a tree that's full of violations and see if I can work them all out. So here's my idea. Instead of starting with an empty heap, let's just make a tree containing all of the keys. We know what the tree is going to look like because we know what a complete binary tree on that number of nodes looks like. I'll just put them all into a tree and then see whether I can fix all of the violations that occur. Okay, so I get this. So I just took every element of my sequence in order. So this becomes the root, that's index 1. So I just sort of put it in there. There's 41, there's 5, there's 92, and so on. I just take my sequence and dump it into my array. And I end up with this. And we can view this as a tree, but it's probably not going to be a heap. In this case, it certainly isn't a heap. We've got numerous heap property violations. So at all of these nodes, there is a violation of the heap property at that node with respect to its children. Although the shape property is satisfied because, of course, if I put a bunch of keys into an array in order, I end up with a complete binary tree by our indexing interpretation. So the question is there a way of restoring the heap property across the entire thing fast? Can I do that faster than n log n time? And the answer is yes, because what I can do is start at the bottom and work my way up. So let's think about this. If I say, let's look at only the nodes below this line. And of course, below this line, I have a bunch of separate small small individual subtrees. Can I restore the heap property for this? Well, obviously, yes. It's a single node. The heap property holds by default. Same here, same here, same here, same here, same here, same here. It's easy to turn all of the nodes on the last level into mini heaps of their own because they're already mini heaps of their own. So what I could do is start at the lowest level and convert subtrees into heaps one at a time. And I'm trying to exploit the logic from my thought experiment, which is that if I have two small heaps and I want to fold in one more element, it seems like it's pretty easy to get that done. And so I want to try and create that process with my tree full of heap property violations. Okay, so I start at the lowest level. And those are easy because they're already heaps. Okay, because a single node is always a heap. Good. Now I go and look at level 2. And at each step, what I can assume is that every subtree of the nodes I'm working with is already a heap. So I now look at the nodes, the subtrees rooted at level 2, and I try and restore the heap property. Well, to do that, what I'm sort of doing is I'm merging together two heaps that I know are valid with one extra element. So I can do this by performing a bubble down operation. So I do that. I perform a bunch of bubble down operations in these tiny heaps. So I bubble down the root of this, and if necessary, the root of this, and if necessary, the root of this, and the root of this. So I do 4 bubble down operations on a heap of height 1, because that's what I have if I'm at level h-1 is mini heaps of height 1. Okay, so now what I have are these subtrees are guaranteed to be valid heaps. And I go up one level and try and do the same thing at level, this would be level 1. So h-2. And I then perform one bubble down operation with respect to its two subtrees at this level to restore the heap property for both of these subtrees. Okay, and then I do the same thing at the root to restore the heap property globally. Okay, so what I've done is a bunch of bubble down operations versus what I was doing with the n insertions, which was a whole bunch of bubble up operations. I guess what my hope is that unlike the insertions, so in the insertion case, once I've inserted half of my values, the tree is already pretty tall, which means that most of my remaining insertions could require log n time, and therefore that I end up with n log n time in total. In this case, though, working from the bottom up, notice how actually very few bubble down operations had to happen at the top of the tree. Most of the bubble down operations I did were on very small heaps, because most of the elements are near the bottom. If I start at the bottom and work up, I do a bunch of small operations on small heaps, and as I get to the top, the number of operations I do on large heaps is smaller and smaller. So the question is there a way I can show this is faster? I'll spoil it and say it turns out it actually is faster. And the reason is because although we did do bubble down operations, which are big theta of h, most of those bubble down operations were performed on smaller subtrees that had a smaller height. So here's pseudocode for my bottom up construction. The name of this algorithm, this is the official name, is Heapify. And we can exploit the way that the array-based heap works to do this with an incredibly simple methodology. So what I did with my diagram there was I started with everything at level 3, the last level of the tree, then I worked up to level 2, then level 1, then level 0. But actually, if I think about this carefully, it turns out that if I want to go through the levels in reverse order, couldn't I just go through indices in reverse order? If I start at index 14 and bubble down, that restores the heap here, then 13, 12, 11, 10, 9, 8, because my indexing sequence was a level order traversal to begin with. So all I really need to do to restore the heap property starting at level 3 and working my way up is to run bubble down on each node in reverse order of my indexing sequence, because that will take me through each level before it gets to the level above it. So Heapify is just deceptively simple. All it is a loop that counts backwards from n. Notice that the last index is n itself, not n minus 1, because we're using 1-based indexing. And then at each step just performs one bubble down operation. And that's Heapify, the bottom-up heap construction. And what's even better about this is, if you give me an array, I just convert the array into a heap directly. I don't bother making a bunch of nodes. You've already given me an array. I'll just use that array to store my heap. So we don't even need to make any extra storage. We're just doing a simple loop that performs bubble down operations. But what about the running time? Okay, this is what I just said. So it turns out that the running time of this is actually big theta of n. I'm actually able to convert the entire array in place into a heap in linear time. And I'll give a proof of that. So the claim is that my Heapify algorithm constructs the heap of n elements with big theta of n operations. And as I pointed out, it does feel like, since the bubble down operation requires big O of h, or big theta of h, and that the height of the eventual tree is log n, that I should need n log n operations. But again, we can exploit the fact that most of those bubble down operations, more than half of them, are done on very, very small trees. So what do we know? Well, the total height of the tree when I'm done is log base 2 of n, for the final value of n. If I look at a subtree rooted at a particular depth, so we have to talk about h minus I, so a diagram might be helpful here. Okay, so in this tree, the height is 3. And if I look at, let's say, a subtree, this would be level 2 here. If I look at the subtree rooted at level 2, the height of this would be 3 minus 2, which is equal to 1. So that's a subtree of height 1. So a subtree rooted at depth I has height at most h minus I. It could actually be a lower height, because if I look at this subtree, which is also at level 2, it actually has height 0. So it has height at most h minus I. That means if I perform bubble down at level I need at most this number of operations, big O of h minus I. And you'll see I'm doing something clever, well, something I think is clever, with asymptotic notation here, just to get around a bunch of special cases. So we already know, because we proved this, that bubble down is big theta of h on a tree of height h. So on my subtree of height h minus I, bubble down is definitely big theta of h minus I. I only need the big O part of it, so I'll just say it's big O of h minus I. What do we know about big O? Well, if something is big O of h minus I, that means that it requires at most c times h minus I operations. Here's the thing where I think we're going to save some time. So I know, since I already have a big O result, I'm allowed to assume the definition of big O is met. So the number of operations is at most c times h minus I for some constant. Who cares what it is? I know that it exists. And that means, so I can then use this as a way of measuring how long each bubble down operation took if I'm talking about a specific level I. The number of elements, the number of nodes at each level, is 2 to the I. So level I contains 2 to the I nodes. If I want to compute the total running time of all the bubble down operations together, it will then be the number of nodes at each level multiplied by this number. So I can condense it down into this sum here. Total number of operations is the sum across all levels from 0 up to h of c times h minus I, where c is a constant that has to exist because of the way big O is defined, multiplied by the total number of things at that level, at most. So it could be less than this, but it's at most this number. Okay, so that's this sum here. And if I play around with it a bit, that is, if I basically reverse my indexing sequence, I can, instead of writing h minus I times 2 to the I can write it as I times 2 to the h minus I. So in a sense, what I'm doing is I'm unwrapping the sum and then wrapping it back up in reverse order. So you can satisfy yourself that this algebra does work out. The reason I'm doing that is because having h minus I in the exponent instead of as a coefficient makes it way easier for me to play with exponents and end up with something that's easier to work with. So anyway, I end up, if I fiddle with this, 2 to the h minus I is 2 to the h over 2 to the I. It's this. And because h doesn't depend on the summation variable, I can pull it out. So I end up with this sum here. And the reason I've done this is the kind of proof where it's not like you'd be able to derive the proof from forwards from the beginning to the end, because I've actually written the proof specifically to try and get to a form that looks like this, because I really want this sum, because it turns out we can use an algebraic identity to get rid of the sum. All right, so there's this identity. Now, I'm pulling this out of nothing here. So this is an identity. We could prove it by induction or something, but I will assert that it is true and it's well known. So I don't need to provide a proof of it, although you could easily write one. It's not the end of the way. It isn't difficult to prove this. So there's an identity that says if you are adding up I over 2 to the I for some sum of like I equals 0 up to k, it comes to be this number here. Which means if I go back to my expression for the running time of Heapify, which is this, I can say it's less than or equal to, well, I did a little bit of extra work here. So what can we say about this thing on the right? So the sum of I over 2 to the I is equal to 2 minus something. And I say, well, this thing is obviously positive, which means the whole thing has to be just less than or equal to 2. If I don't subtract something, the number is going to be bigger, which means I can say that this summation is at most equal to 2. So therefore, I can reduce my running time down to this thing, c times 2 to the h all times 2. And then I plug in, because I know in my heap that the eventual height of my heap, so like the full height of all after all n elements is inserted, is at most equal to log n. So I just plug that value of h, or that upper bound for h, into this expression, and I end up saying, okay, well, c times 2 to the h times 2 is c times 2 to the log n, which is just 2 times cn. And that means that Heapify is linear time. So if you give me n elements and I use my bottom-up heap construction, I can create a heap out of all of them in linear time. That's a big deal. However, we're about to talk about the sorting aspect of heaps, and it turns out that it doesn't give us a better running time than n log n. So although we can insert all of the elements in better than n log n time, RemoveMin still takes log n time because we start from the big heap and work our way back down. And there it is, our character select screen, maybe for the very last time. It's finally time to meet Heap Sort. It's finally time to get to know that mysterious stranger. So probably we already know what to expect here. We know that we saw at the very beginning, if I have a priority queue, I can insert n elements and then remove them all in order, and that gives me a sorted representation. And that would be, in the case of a heap, I do n insertions, each one takes at most log n time, or I do better if I use Heapify, followed by n removals, each one takes at most log n time, and so it's n log n time in total. It happens that I'm actually able to do this with no extra space because I can just create the heap on top of the array you gave me. And I can actually turn that array, or that heap, back into a sorted array without needing extra space either. I'm going to talk about that aspect next. But certainly it's pretty clear by now that I should be able to sort with a heap just by doing insertions and removals. So there's Heap Sort. I mean, at this point, it's pretty straightforward. I make a heap, so you give me an array. The most basic version of Heap Sort is I make a heap, and this would be a version that does use extra space. I then insert every element of my array into the heap, and then I go back through my heap, I call RemoveMin, and just pull out the element and stick it in the corresponding index of A. And that's it. All I need to make my heap into a sorting algorithm is sort of this little adapter that I install on top of it to turn it into a sorting algorithm. And the running time is n log n, and that's pretty obvious at this point because we know that each of these operations is log n, and we're just doing them inside of loops that take n operations, n iterations, and that's n log n. If I were to use Heapify instead of this business, well, then I could take this whole step down to n by not inserting each element individually. The problem is this thing would still be big theta of n log n. Okay, so too bad, heap sort is still n log n. That shouldn't surprise us one bit because it's impossible for heap sort to be any faster than that. We already know that because it's a comparison-based algorithm, we cannot do better than this in the worst case. It would be impossible for a heap to ever allow us to sort n elements with comparisons in big theta of n time, or in better than big theta of n log n time. So I still need n log n time even if I use Heapify. That's too bad. That doesn't mean Heapify is a bad idea. If you want to write heap sort, you still want it to be fast, right? So you might as well use Heapify because it does save some time, but you can't break the n log n barrier. It actually turns out as well that there's a way of performing heap sort without making an extra array, with just doing everything inside of the array you started with, other than, I suppose, the need to do the one-based indexing, which is an external concern for my purposes, because that's just one extra element that we might be wasting. And the trick is we actually have to switch to a max heap. And we end up doing a trick that's very similar to what selection sort does. It's actually a sort of neat reversal of selection sort's trick. So what we do is we begin, you give me an array, and I just treat the array as if it's already a binary tree. So I do similarly to what we do with Heapify, and then I run Heapify itself. So I begin by taking your input array, and I run Heapify on it to turn it into a max heap. And hopefully you can agree that rewriting our heap algorithms as a max heap version, it doesn't take any real work. It just means flipping all of your comparisons. So I use Heapify. Here it goes to make my thing into a max heap. Okay, so it's doing the bubble down operations. Now I have a max heap. And so that means the root of my max heap contains the largest element of my collection. And I think to myself, where would my largest element go when I'm done? Well, in the sorted representation, of course, the largest element goes in the last position. Okay, interesting note. Okay, second thing. How do I actually perform one more step of heap sort once I have my heap? Well, I do a RemoveMin operation. Okay, let's think about this. When I do a RemoveMin, what element of my array gets freed up? Well, I'm going to delete this leaf, put the 26 over here, and then element 13 is no longer needed. Index 13 in my array is no longer needed. Well, what a coincidence. That's exactly where the number 97 would go. So what I observe is that because I'm using a max heap, as the heap shrinks, the positions of the array that it frees up are exactly the positions where the maximum element goes at each step. So I now perform a series of remove max operations, because in a max heap you have remove max instead of remove min. All right, so I remove the number 97, so I remove the current value of the root, I perform a full bubble down operation, and then I stash the value I removed in the freed up position that was vacated by that last node. Now, you could formally think, well, actually, we could still consider this to be part of the tree, but it's not really there. It's sort of a ghost. And so I'll just draw the node with this sort of ghostly representation, because it is still part of the array, and so it's still subject to my indexing scheme, but I don't use it. So of course, as far as node with index 6 is concerned, it only has one child. But I will draw in these things as I fill them in to make it clear what I'm doing, the kind of swaps I'm performing. Okay, and so I then do another RemoveMin, and I stash the removed element in the vacated position at index 12, and I just keep doing this. And of course, we know that heap sort is n log n, and what we're doing here doesn't change the running time at all. I'm just taking advantage of empty space. Maybe you can see why I needed a max heap for this, because I do still need index 1. And a min heap, if I free up the minimum element, I would want to put it at the beginning of the array, whereas in a max heap, I'm freeing up elements, indices at the end, and those are exactly where the maximum element goes at each step. And just like in selection sort, once I've finalized what's in position 7, I can pretend like none of this stuff was there to begin with. And I can pretend like I'm starting again from scratch with what remains. So when I remove the number 31, it goes in the last position of what remains. And I just walk all the way back through that, and soon enough, I've got my sorted array. And that would be my in-place version of heap sort. And if you look at a typical implementation of heap sort, it would work probably like this. So it's in place because it saves on extra copy operations, and it uses Heapify to streamline the process of turning what I started with into a heap. And that's sorting. I think that's all we have to say about the general comparison sorting problem in this course. We'll, of course, need some sorting over time as the course continues. We'll talk about various generalizations of sorting, but I think that finally completes our coverage of sorting, and we're now ready to just dive in to talking about data structures based on trees. I want to have a couple of last notes to wrap things up, though. So one of them is, we know, of course, that any comparison-based sorting algorithm requires big omega of n log n operations. That means, because we've just shown that heap sort can achieve that bound, that heap sort is asymptotically optimal. So in this course, we have met two asymptotically optimal sorting algorithms, merge sort and heap sort. It is true, as I mentioned last time, and I have observed this before, that heap sort in practice can often require more constant time overhead. Part of that has to do with the bubble down operation, which needs to make extra comparisons, I guess, than may be needed. However, it is possible to optimize heap sort. So I have to be clear about this. Just because it requires more comparisons doesn't mean it's always slower. There could be other ways it could save time or space. And the ability to perform heap sort in place is a huge bonus. Merge sort can't generally be performed in place. Let's go back and find, it's going to be quite a ways back through this animation. If we go back and look at our character select screen, we should fully appreciate the different properties besides running time of our algorithms. So heap sort is n log n, that's great. The extra space it requires is constant because we can do it in place. We do not have that benefit for merge sort. On the other hand, merge sort can be written in such a way to be stable by default. So two elements that are equal, that compare as equal, will remain in the same order in the output as in the input. Heap sort by default doesn't give us that guarantee. And that shouldn't surprise us because as we perform the heap operations, elements get thrown all over the place. Of course, it is possible to convert any sorting algorithm to be stable by modifying your comparison operation. So we can always make a stable heap sort. It's just that heap sort can't be made stable by default for free with no extra work. And so heap sort's beneficial if you want an n log n algorithm that's in place if you're willing to sacrifice stability or do a little bit of extra work to achieve stability. Additionally, even though heap sort might require more constant time overhead in a typical implementation, somebody who's an expert at optimizing sorting algorithms might still be able to write a heap sort that is pretty competitive with merge sort in general. So keep that in mind. There's no guarantee, because in this course we don't talk too much about that low-level optimization aspect. There's no guarantee that heap sort is always slower, but I will say overall, rule of thumb, you can expect merge sort to be a bit more lean or efficient or whatever by default. And also one other note about sorting is that in practice, in a library implementation of a sorting algorithm, often a combination of different algorithms are used. We've seen, for example, that in a divide and conquer algorithm, a lot of the biggest advantage of the divide and conquer happens early on. When I get really far down in my splits, down to splitting arrays of size 2 into size 1, a lot of extra work is being done to split and merge for a very small number of elements. So a very common trick when implementing sorting algorithms in practice is to combine them together. To perform merge sort until you've got subarrays of size, 10 or something, and then use insertion sort. Then use an algorithm that has other benefits. Insertion sort is n squared in the worst case, but insertion sort on an array of size 10, or maybe heap sort or something similar, has other advantages. For example, that there's less overhead of the copying or recursive calls you would need with merge sort. And so if you look up sorting algorithms, you will discover a lot of variants on sorting algorithms, including the ones that are used in practice by popular standard libraries, are typically combinations of different techniques, including combining n log n algorithms like merge sort or heap sort with other algorithms that may not actually be n log n in the worst case to accommodate certain cases and optimize the algorithm. And the same is true of quicksort. A lot of libraries actually use quicksort as the sorting algorithm, but they add special guards to it to catch cases where quicksort is taking too long. So for example, they might allow quicksort to run for the first 10 levels of recursion. And if quicksort takes too long, then they switch over to a different algorithm to clean up the mess, because we know that quicksort can in some cases make a bit of a mess. It can take n squared time. So all we've done in this course is talk about each sorting algorithm unto itself, talk about the asymptotic running time. If you have to implement and optimize a sorting algorithm, there's a lot more work to it than just choosing asymptotically good algorithms. That's certainly very important, choosing and understanding those algorithms, but optimizing it for practical performance requires things that go beyond that. And that's because, of course, what we're talking about here is a discussion of algorithms at a high level. When we get to optimizing and implementing things, that's a much more low-level conversation that goes far beyond the study of algorithms in the abstract. And just at the end, one last exercise. This is an exercise relevant both to this lecture and the previous one. Prove, well, I don't know what you might use to prove this, although it's sitting on the slide with this theorem. Prove that it is impossible to design a comparison-based priority queue which gives you these running time guarantees. So remember that our lower bound on comparison sorting makes a statement about any comparison sorting algorithm that could ever exist. And those are difficult to make. That's a profound result, making a statement about anything, even things that haven't been invented yet or that we don't understand. I'm asking you to write a similar proof about the priority queue structure. Prove that it is impossible for anybody now or ever in the future to develop a priority queue using our methodology of a comparison-based system where the running time of both of these two operations is log n. We know that it's possible to get insert or remove min down to constant if the other operation is slow. But I'm saying prove that you could never have both of these two things. That would be too much of a perfect world to realize, and it's impossible. All right, and so next we're going to begin talking more about uses of trees and more uses of trees as data structures, but we're finally ready to move on from comparison sorting.